So welcome everyone to the second workshop on correctness and reproducibility. Some of you were here yesterday. We had a great tutorial day. Alper did an excellent job organizing and we had some really nice talks. That was fun. My name is Allison Baker and I'm one of the co-chairs, and Alper Altuntas, who's sitting here in the front, is the other if you want to wave. So this is the second edition of this workshop. The first one was 2 years ago, and we thought it went really well. And some of you were here and some of you are new, and welcome. The funding for this time, a lot of it came from the Better Scientific Software Fellowship program that Alper applied to and was awarded, and that's how we were able to do the tutorial. And this morning session is kind of joint tutorial and workshop. So we really appreciate that support. And we've also gotten general support from the Climate and Global Dynamics Lab, where Alper is a part of, and the Computational and Information Systems Lab, which I'm a part of. So as I said, Alper and I are the co-chairs. A lot of committee members are here. We thank them for their help. Dorit is here in the audience. Brian was here yesterday and I'll be here later. Ganesh is up here. Karsten, I believe, is online. Balwinder will be here. He was here yesterday. And thank you to all of you. And of course, thank you to our administrators who are invaluable in making this happen. I just want to say a few things about the first workshop. If you missed it, there's a link to it from the current workshop page, and all the slides and recordings of the talks are still there. If you're like, well, this one is great, I wonder what happened last time. And you have like tons of extra time to watch videos. I also wanted to mention that we did, Alper and I, along with the committee, write up kind of it was a technical report that was kind of a summary of the themes and talks from last time, and kind of some of the key takeaways from the workshop as far as like identifying the challenges and kind of, you know, opinions, solutions, future directions. I don't think we've talked about if we're doing that again this year, but we'll think about that later. So a few things, this is being held at NCAR, so the code of conduct is pretty straightforward. You know, let's be considerate, respectful, and collaborative. We value a diversity of views and opinions, and we really want everyone to feel comfortable participating and expressing themselves. The workshop program is on the website. You can scan that QR code. After the workshop, and by after I mean like maybe in a week or 2 weeks or something, maybe after Thanksgiving, sometime we'll post the recordings of the talks and the slides. So that will be available. Today we have a 30-minute break mid-morning and mid-afternoon, and we hope you'll use that time to, you know, introduce yourself to someone that you haven't met and discuss things. Again, everyone's encouraged to participate. If you're remote, you can use the raise hand feature. You can also put questions in the chat. There will always be someone moderating the chat who will then read the question for you. And in person, during the question and answer session, the microphones on the ceiling will be on, so we won't need to run and bring you a microphone. When we call on you, you'll just be able to talk. Okay, here are the important things. Lunch. So if you weren't here, if you were here yesterday, it's going to be the same today. You can follow the crowd around to the cafeteria, go through the line. It's self-pay today, but there's a reserved area. It'll be on the left side of the cafeteria after you go through the line for workshop participants. So again, another social networking opportunity. Tomorrow, the regular cafeteria line is closed, so we'll be providing everyone lunch in the same location in the cafeteria. And then tonight, after the meeting, so around 5, we're hoping that if you're in person, you'll consider joining us for happy hour at the Southern Sun. Alper and I will be there. It's down at the bottom of the hill. They do take cash only, which is kind of retro and weird, but there's an ATM machine in there, and there's 2 banks, you know, right around there too with ATMs. If you need a ride, plenty of us have cars, can take extra people, so we'll kind of like gather out in the lobby. So if you either need a ride or you are able to take someone, then we'll kind of gather out there. And kind of right before the morning break, I'm going to ask for a show of hands if you think you're going to go, just so we can call ahead and say, how many of us are going to show up. And of course, if you raise your hand and I'm not wanting to go, or don't raise your hand wanting to go, that's totally fine. We just want to get an estimate. So with that, these were my exciting opening remarks. And this morning we have our keynote speaker and 2 invited talks. And there'll be a little bit of time for questions after each of those, but then we're going to have a panel with the 3 speakers that Dorit's going to moderate, and there'll be lots of time for discussion then. So anyway, I think we have a good lineup for today, and thank you for coming.
So it's my pleasure to introduce our next invited speaker, Antonios Mamalakis. Antonios is an assistant professor of data science and environmental sciences at the University of Virginia. He received his PhD from the University of California, Irvine, and his research spans statistical analysis, machine and deep learning, and explainable AI, applied to challenges in environmental sciences, including hydroclimate, extreme events, teleconnections, predictability, and climate attribution. So with that, Antonio, please take it away.
Thank you. Thank you very much. Thank you everyone for being here this morning. And thank you to the organizers for putting together this very exciting workshop. I'm really looking forward to learn and see how these next couple of days go. Yes, so I'm very glad to be here. Thank you for the invitation. I would like, is everything? I would like today to talk about explainable AI. And when I would like to reflect together with you on when explainable AI results are reliable in environmental applications. This is the main question we want to think about in the next 30-35 minutes. And just to see where we are in the room, how many of you have heard the term explainable artificial intelligence? Okay, 60-70%. Okay, I have a brief introduction, so all of us will get on the same page. So what is XAI, explainable artificial intelligence, and why do we need it? Let's start from there. Well, the answer to why we need it is fairly simple. In environmental sciences, in geosciences, apart from caring about the performance of an AI model, we also care about if it is making the correct predictions for the right reasons. That's a big thing in geosciences. We want to know what's going on under the hood. So XAI stands for this. It is an umbrella term that includes all these different methods that can be used in a post-prediction setting. And we can start learning about how the AI system we have built makes predictions. So let's look at this very simple example, which is not related to geosciences, but I'm starting with a nice example so we can all get on the same page. So here we have trained the neural network to classify different images. And this network is telling us this image, this input image in this case, is an image that shows a junco bird. Well, I don't know what junco bird is. It's a bird. Yeah. Now, the important thing here is not really the prediction. The important thing is what are the features, what are the patterns on the image that the network used to make the correct prediction. This is where this explainability comes from, okay? This is what it means. And this is a very famous example. Again, there are many methods of XAI, but one famous and popular subcategory of methods is what we call feature attribution. And this is an example right here. We use a method to get a heat map where the patterns that are useful to the network are being highlighted in this heat map. So in this example, the network, based on this XAI we're using to open up this black box, the network was using the eye of the bird and the mouth of the bird to say, this is a junco bird, I know that. Let's see another example. Here we have trained a different CNN to classify handwritten digits, numbers. So you can see for different examples on the left, different inputs, the network is classifying correctly these inputs. And also you can see why. You can see the reason. And if we focus on this example of a 0, the pixels also in the middle of the input that are they're not black. The lack of black color in the middle is also important for the network to say this is a 0. Same thing with the 4. The fact that there is no horizontal line here at the top helped the network to say this is a 4, it's not a 9. Because if there was a horizontal line there, that would have been a 9. Okay? Now, with this tool, with these XAI tools, we are starting to get an idea how the models decide. This can be a game changer for us to use AI for science. Because in science, again, we need to know how the model decides. Now we are getting to the environmental science or climate science applications of XAI. And there are many. I would say there are hundreds of papers applying XAI in climate science since 2020 or something like that. So this is an example from a paper by Toms et al. In 2021. The authors are using sea surface temperature maps, sea surface temperature anomaly fields over the last year or so, the last 9 months or so, to predict the surface temperature over land on decadal timescales. And the important thing here, you can see how the model performs on the right, on the top right. This is the performance, the accuracy of the model around over different regions. But the important thing is that for each and every prediction that we make, we can ask the network, we can use these XAI techniques and say, what are the patterns that help you make a prediction over here? And you see, the tropical Pacific arises as an important pattern that the network was using to make a prediction, okay? Now, I hope these examples help everybody to know or to get familiar with what XAI is. Specifically, the subcategory of XAI that we call feature attribution or attribution heat maps, right? Now, the next thing I want to address is there are many XAI techniques out there. How do we know which XAI method is better? That's the next thing we will look into that. We will look into. Let's go back to the Janko bird example. As I said before, this is an XAI heat map, an attribution heat map. You can use either term. And the XAI, I didn't tell you before, but I'm telling you now, the XAI that I was using before in the schematic is an XAI method that's called guided backpropagation. The details of this method are not important at this point, but it is a popular XAI technique. And again, it's highlighting the eye of the bird as an important feature for the network. I have a question for everybody here to reflect on. How can we know if these are actually the patterns that the network is using? Can we know that? How can we know that? Essentially, it's a problem of non-falsifiability. In other words, there are ways to assess how trustworthy this explanation is, but on a theoretical level, it's like trying to test if a translator is doing a good job when you don't know the language, right? So some people have highlighted this issue of we don't have a ground truth of the explanation as the issue of XAI being non-falsifiable. That doesn't mean we cannot work around this issue and assess the explanation, but we need to keep in mind that there is no ground truth of XAI. The second problem is that, as I said before, there are many XAI techniques out there. Almost every computer science lab in every university around the globe can derive an XAI technique, right? If you apply all these different techniques, and there are dozens of those, to the same network and the same prediction, so everything is the same, we just want to explain how the network is deciding, you will get different answers. and sometimes very contradicting answers. This method, which is also a very popular method, integrated gradients, and I like this method. I mean, this is my personal bias, but this method is highlighting the belly of the bird. The belly of the bird doesn't show up at all in the other method. Imagine if this was a pattern in the Pacific. Imagine if this was El Nino. Was El Nino important in the prediction or not? This is the same network, okay? So there are issues. And those two issues, the issue of no ground truth and the issue of high inter-method variance, high inter-method variability, makes us need to come up with ways to objectively assess these methods. We came up with a way to do that a couple of years ago. And what we did is to essentially try to derive synthetic data sets, synthetic outputs and synthetic inputs that we know the relationship between that connects them. If we know the relationship that connects them, then we can essentially derive a ground truth. So here are the steps. The first step is to just generate synthetic inputs. Again, here the inspiration is from a climate prediction setting. So I have generated 1 million maps of what is supposed to be an sea surface temperature anomaly field. So these fields are fake, they never happened, but they resemble the statistical properties of what a sea surface temperature anomaly field looks like. So the covariance is the same and things like that. This is the synthetic input. Then I'm using a function f here, which I don't have the details to go through, but it's a known function that I have chosen, and I map each and every one of these maps into a scalar value. So I'm creating a target, a synthetic target. And because I know f, I can derive the ground truth of the explanation. I can derive how much each of these pixels contributed to each and every y value here. So in step 3, I can pretend I don't know f, and I can use a network to train and try to predict y given x. And once I have done that, I can benchmark all these XAI techniques. And because I have 1 million data sets, data points, I'm able to achieve a very high performance in the network. So here is an example. If we focus on this example of y being 0.066, and the network prediction in this case was 0.0802, we can have, again, because we know f, we know the ground truth of the attribution. So pixels that you see here in red positively contributed to y. And pixels that you see here in blue negatively contributed to this y value. In other words, if it was not for these blue pixels, the y value would have been higher. This is what we get when we explain the network prediction. And look at that. The different methods give different heat maps. Now, in real applications, we never have this ground truth. We trust what the XAI gives us. And there are methods that give totally irrelevant things to what the true drivers are. Okay, that's something to highlight. But again, there are some methods here, 4 methods that I have chosen that are approximating this ground truth fairly well. So the correlation of this heat map to the ground truth is 0.82. The point that I'm trying to make here is not about the methods themselves, but it's about the benchmark. We have created a ground truth of explanation. So we are no longer in the dark. We have a way to test the translator, right? Okay, and here now I want to get into a more interesting part of the talk. And I want to assess these XAI techniques under realistic conditions. Because so far we have been considering 1 million samples, and we have been considering a target, this Y target that has 0 noise. That's not realistic, right? So let's start adding noise to the target and see how these XAI techniques behave, how much they mess up, okay? I want to acknowledge the help of my collaborators here, and many of you are familiar with these people, with these scientists, Will Chapman and Kirsten Meyer. They're NCAR people, NCAR scientists. So I wanted to give a shout out to them. These results of this work are out on a preprint for those who are interested. Okay, so what we did is that apart from this noise-free target that we call Y, and it is unrealistic, we create three alternatives. One target that is a little bit noisy, so we add a noise where the standard deviation of that noise is only half of the standard deviation of the original Y. We have an alternative target that is moderately noisy, and then we have a target that is highly noisy. And for each one of those targets, we train two models. One model with 100,000 samples, one model only with 1,000 samples. And what we want to explore is how the XAI results, how reliable they become with noise and with limited data. Because this is the reality in climate applications. Okay, so we have totally 7 models, 6 models, data rich and data poor models for each one of these realistic targets, and one data rich model for the noise-free target, which is already unrealistic. So, but we have it as our ceiling point, essentially. The first thing we looked at, performance. And we measure performance by the degree to which the model can capture the variance in the target. And I want to highlight that the model here that we're using, the network, is a transformer, a vision transformer, but the architecture is exactly identical in all these cases. The only thing that changes is the noise and the data we use. Look at that. So the idealistic scenario, the model that is trying to predict a noise-free target and with lots of data, it's capturing 99% of the variance. That never happens in climate applications, right? Never happens. With the slightly noisy target, the R-squared drops. And the more the data, the higher the R-squared. And when we go to the highly noise target, the R-squared drops even below 10%. Now, this controlled set of experiments gives us the chance to explore all these models now. And we range from models capturing almost 100% to models capturing 9%. And guess what is happening with XAI here? Okay, let's see. Let's focus on one example, and I'm using here integrated gradients. This is the input to the model. This is what the ground truth of the attribution should look like. This is what we get from the XAI for the model, the idealistic model, the noise-free data-rich model. You see, it can very well recover the patterns of and it resembles the true drivers very well, right? This is the ideal case. The correlation between this heat map from the XAI and the true drivers is almost 0.9. That's good similarity, okay? Here are the data-rich models with increasingly more noisy targets. You see the correlation drops. The correlation with the ground truth drops. But the important thing is that even for this highly noisy target, this model that captures only 18% of the variance still relates a little bit to the ground truth with a correlation of 0.44. What is happening with the data poor models? It's a mess. Look at that. It's a mess. And the important thing here is that this model was capturing 57% of the variance. Now, wait a minute. In my experience, whenever I have a model that captures almost 60% of the variance, in some cases, I think that's a decent model. I should look into it and learn from it, maybe. No, you shouldn't. According to this controlled, R-squared is not a good proxy for XAI fidelity. It's not at all. Because this model that captures much less of the variance, lower fraction of the variance, it's a better XAI model to, a better model to apply XAI on. Why is that happening? Well, let's see another example to see if that is the case indeed. Indeed, it is the case in a second example here. Is it the case that, is this the case because of the method we're using? Let's explore that. It turns out, no. All the methods except from the gradient, because the gradient method quantifies sensitivity. It doesn't quantify attribution. But all these other 4 methods, input times gradient, integrated gradients, occlusion, SAP, these are very popular methods. All of them correlate well with the ground truth for the noisy free data rich model, but for the data poor models, look at that, 0 correlation. In other words, these are squared. Although it's close to 60%, the explanations are irrelevant. That's a real problem. And why is that happening? Here is the answer. The answer is that those experiments that we kept adding noise, by adding noise, the learnable variance changes. So you can very easily prove that for the experiment with the low noise, only 80% is of the variance is learnable. 20% is just random. 80% is learnable. Well, so if we go back to our R² values and we account for the fact that in this case, 80% is learnable, well, a model that captures 78% out of 80%, that's a good model. But a model that captures 57 out of 80, that's not so great. In the same way, a model that captures 18% out of 20 that is learnable, that's a good model. It's a better model than this one that captures 57 out of 80. That's why we need to rescale those R² values, accounting for the fact of how much of the variance is actually learnable. And when you do that, you see that these 3 models score very highly, and that's why they are more relevant for XAI. This is why these models, the correlation to the ground truth was higher for these 3 models, But the problem is that in real life, we never know how much noise we have in the data. That's the problem. And we don't know how much of a sample size is sufficient for us to get to a point where we have learned enough of the learnable signal. We don't know that. So what do? We need to come up with proxies. And we have used some proxies, and I'm presenting the useful ones, okay? The first useful proxy is the inter-method XAI consensus. So I will be plotting here the XAI agreement to the ground truth on the vertical, and on the horizontal axis, I'm plotting the XAI consensus across different XAI techniques, okay? What do you see here? Surprisingly and very interestingly, all the models, all the predictions and the explanations that belong to data-rich models form a cluster here. And all the models that come, all the predictions and explanations that come from data-poor models form a cluster, a separate cluster. And the interesting thing about this cluster is that the more they agree with each other, the more likely they are to have learned something, the more likely they are to be agreeing with the ground truth, which means that they know when they know things. That's, in psychology, it's called metacognition, right? But these models, these messed up models, they are ignorant. They are epistemically, this is what we call them in the preprint. They're epistemically ignorant, which means that they don't have metacognition and they don't know when they don't know stuff. You see that even for predictions that they relatively agree more than other predictions, even for those predictions, they don't correlate with the ground truth. So in real life, when do I know if my model has exited this epistemic ignorance? When do I know that? Here's another proxy. Here I'm plotting not the inter-method XAI consensus, but the intermodal XAI consensus. And you see the same pattern. For models that are knowledgeable, there is a linear structure of consensus. For models that are not knowledgeable, there is nothing there. And so when you plot then the intermodal XAI consensus and the intermethod XAI consensus together, you get the same thing. And we argue that this can be a meta-diagnostic. If there is a linear structure in the consensus of the XAI heat maps, then you can assume, it's not a sufficient condition, but at least it's a necessary condition for you to assume that maybe your models have learned something, okay? So I think I'm doing well with time. If I want you, if you can keep 3 things from this talk, 1 key point for every 10 minutes that you have listened to me. The first thing is we need more objectivity in this XAI field to address the non-falsifiability of the XAI and to address the intermethod variance. So we need objective ways to assess these methods and assess these results. The second thing, a high R squared or a low R squared, the raw value of an R squared doesn't really mean anything about XAI fidelity. It can be, because you can have a model that captures 10% of the variance out of 12% of the variance in your data that is learnable. If it's capturing 10 out of 12, that's a good model. But if it's capturing 50 out of 90, that's a bad model. You shouldn't apply XAI to learn from it. But because we never know how much is learnable, we need proxies. And these proxies, we argue, a good proxy is structure in the consensus. Not necessarily consensus, but structure in the consensus of XAI. And I will finish with this quote and the preprint. If you ever wonder whether your AI has truly learned anything, don't look at its accuracy. Just build an XAI ensemble, meaning many models, different architectures or different training seeds, many XAI methods, generate many heat maps, and assess the structure of the consensus within that XAI ensemble. So build an XAI ensemble and look at the consensus, the structure in the consensus. That's the key takeaway. And with that, thank you very much.
Questions?
I got one.
Sure.
When doing these experiments, one has to worry about whether the VLM you are using itself suffers from non-determinism, because people have observed that even with 0 temperature setting, sometimes they don't reproduce.
Right.
And there are reasons for that.
Right. That's a very good point.
We are currently validating these results across different architectures, not only VLMs, going from very simple feed-forward multiple perceptrons all the way up to more sophisticated architecture. So we can test the validity and the robust of these conclusions. Yeah.
Do we have any online questions? They can raise their hand if they're. DJ?
Yeah, this is a really, really interesting result. One thing that strikes me is I've been looking at models that say I can predict aleatoric and epistemic uncertainty as an output. And you showed that in the ensemble case, there seems to be some correlation with the how well the model ensemble classifies the epistemic uncertainty, and then and the XAI robustness. Do you also see like I guess you started looking at things like an evidential model or other models that kind of can do other estimates of their own epistemic uncertainty with this data poor and data rich case and see how they do you see the same pattern?
Yes. So in this case, we have explored models that do not model the uncertainty. But I would say that in the case where the model models predictions is essentially instead of a point, it's a distribution, in which case it should learn to model the uncertainty. Then I think the XAI techniques the consensus can be even more robust there. And using XAI techniques can be even more informative in that case. We haven't explored models that model their own uncertainty to see how generalizable these conclusions are. But yeah, this is something that it's a good next step. We were thinking about doing that with Kirsten. Yeah.
Great. Any other questions? Pretty good. Cool. So we are going to have a 30-minute break now, right?
Ask about who wants to go to the.
Oh yeah. Do you wanna?
Thank you very much. So if you came in late this morning, maybe you noticed on the schedule that we're having a happy hour down at the Southern Sun around 5-ish today. So basically, I think the last talk finishes today at 4:40, and we'll meet out in the lobby if you need a ride or offering a ride. So right now is just hoping for a show of hands if you think you might go, just so we have an estimate of like, how many of us will be. And you can change your mind. Okay, perfect. So we have a half hour for a break, so we'll start back up at 10:55, and there's snacks and stuff out there.
Right. Our next invited speaker is David John Gagne. DJ is a machine learning scientist and head of the Machine Integration and Learning for Systems group here at the NSF NCAR. He earned his PhD from the University of Oklahoma, and his research interests include machine learning systems for applications across Earth system science, including predicting high-impact weather, parameterization, emulation, and explaining ML predictions. With that, please take it away, Peter.
Thank you, Alper. Thank you, everyone, for coming. So today, kind of through the keynotes, we've gone from the, I would say, very theoretical to kind of the kind of theoretical. Now we're going to go very empirical with this talk with a little bit of equations. So there'll be lots of maps for those who enjoy that. First, I want to thank our whole credit team that's been like heavily contributing and making the work I'll be showing possible. And a lot of the research I'm showing is I especially want to thank Yinkai Kyle Shah for all of his efforts on this. Because he led the papers that we'll be covering today. So we're going to go back in time a little bit to like kind of the recent history of AI weather prediction from a full model emulator kind of weather prediction. We've obviously been doing AI weather forecasting of various sorts since like the 1980s, but kind of starting around 2019, 2020, we started getting some people thinking about, hey, like deep learning models seem to be able to do lots of things. Can we have them actually predict the whole state, not just like a parameterization or a post-processing correction? And this became more possible with the basically the release of Error 5 and Weather Bench that came out around early 2020. And there were a few papers kind of in the space that were like trying some initial things on those data sets. And then we get to about 2020, early 2022, we had two papers come out within a week of each other on the archive. The Kiesler et al. Graph neural network weather prediction paper and the ForecastNet paper. And both showing like better performance than GFS. So we're still not at, like on this chart, IFS is at the 100 line. That'd be equivalent to IFS performance on Z500 RMSE at 3 days. And so people got like, this is interesting that we were expecting it to go this fast. And then fast forward to the kind of end of 2022, we had two more papers come out that really changed, I would say, the field and basically the Pengu weather paper and then GraphCast both showed better performance than the IFS, and other people were able to replicate that. A bunch of other groups also released their models, and we've seen kind of an explosion. So also at the end of 2022, there was another
large model got a public interface around it. In November, we had the release of ChatGPT. So kind of right around the same time, while ChatGPT was like kind of like turning over the entire world, the weather world was also seeing that, plus GraphCast and Pengu. And so a bunch of other groups kind of got into the mix. And we've had an increasing diversity of models, all still using ARA5 for the most part. But what we haven't necessarily seen is overall much improvements in performance beyond kind of that slightly better than IFS, now slightly better than IFS Ensemble with some of the ensemble approaches. And we have other reasons to be maybe concerned about where this is going. There's a paper from 2024, Perez et al., looking at a particular like kind of large scale extratropical cyclone case. And we're basically analyzing like the ARA5 representation of the storm at different levels and looking at different features and then comparing that with the IFS versus all the other models. And while some of them capture some of the features, a lot of them are missing key components of this across levels. Like some of them, the winds aren't as strong, for instance, or the temperature gradients aren't as sharp. And this is something we've seen in other verification studies where they can get the location of lows and stuff, but the intensity and the internal consistency of the structure is not always there. And so that's where I think there's a lot of room for potential improvement if we can actually bring in more physics into our design of these AI models. So there's a few groups that have been thinking about this. One approach is to do like a really hybrid approach like neural GCM, which has a traditional dynamical core that was coded up in JAX, plus a neural network physics parameterization. So you just have a giant neural network that does all the physics. And that kind of works, although it's been, it tends to be a bit more unstable than a traditional model. There's also an interesting paper that came out late last year called CLIM ODE, that decomposes prediction into neural ODEs for different like advection and emissions and local and global state updates. And while they ran it very coarsely, they had some interesting ideas of like, if we decompose the problem, we actually get better performance compared to the all-in-one sort of approaches. There's also the Aurora Foundation model, which didn't explicitly use, I would say, physics like equations or whatever, but they did have some interesting features like including the area of the grid cell and their latent representation and actually having different networks that would handle kind of vertical representation as well as horizontal representation kind of built into that. There's also the HealPix grid family of models that Dale Duran originally, I would say, popularized in the weather and climate community, which have nice properties around every cell is an equal area and has consistent directionality. So you can get better performance just from switching to that HealPix grid, even with a relatively simple model. The issue with a lot of these is like in some cases you have to change your architecture quite considerably, or you have to go through a very labor-intensive effort to write a die-core in JAX, which is like the one in neural GCM took like 2 years to write. So what if there are ways to add physical constraints that are more architecture agnostic? And so we're going to talk about some ways that we've been working on here at NCAR in my Miles group on how to do that and how that performs and how it helps and how it may not help. So the framework we've been using for this is something we've developed in-house called CREDIT, or the Community Research Earth Digital Intelligence Twin. The idea behind it is we want to have an open foundational research platform for developing AI Earth system models. So we can basically experiment not just with like, oh, we want to change the architecture, but we want to change what data we're bringing in, how we process that data, how we add physics anywhere in the process. But we're going to, for this talk, we're going to focus on kind of after the model. And then do different kinds of processing and have it all in Python. And eventually we're trying to move everything into like neural network language stuff so you can back propagate through everything. But basically having this flexibility to just try things out and do so in a scalable way that's still easy to use and aiming at kind of like get your grad student, if they want to play around with these kind of models, use CREDIT. You can get training on our NCAR supercomputers really fast and try different experiments and go to town. And the pipeline is fully open source and we're openly developing it. So anytime you see us push stuff, it'll pop up on there. There'll be no release schedules on that. And you can go look at the source code right now. It's on, we're continuing to do new updates and releases. So check it out. So in physics conservation, so this first part will be from a paper that just came out in James on Monday. So you can go search for that. Basically, the idea behind this is we wanted to take an existing AI weather prediction model, in this case, the Fushi model, but it could be any other architecture out there that's in PyTorch in this case. And we wanted to basically apply some things to make sure that the model obeys global conservation. So this means that like the amount of dry air mass over the globe should not be changing from time step to time step. Certainly over very long time scales, that might not be the case, but generally it's you expect the amount of air over the earth to remain constant. Same with the moisture budget conservation. So like anything that precipitates out or evaporates out, like things should generally balance out and be maintained. Although, yeah, there can be complications with some of that. And then global total atmospheric energy should also be conserved as far as it goes with like how much solar energy is coming in and whatnot. And so the way we're doing this is we apply these as what we call post blocks on top of the original architecture. And we add other variables to our models as some as prognostic, but a lot as diagnostic that allow us to calculate budgets or other terms like precipitation and evaporation is just output by the model. And then we can backprop through that and update the rest of the model. We also do we apply these corrections in this particular order during both training and inference, and I'll show you why that's important a little later. And the way we do the adjustment in each of these, I would say, is to we just multiplicatively scale. We take the initial condition values from error 5 for these quantities over the globe, and then we calculate the ratio of that with the predicted values, and then scale certain fields to get everything back in line again. And we just repeat that process throughout training and throughout inference. And so it's like what goes into the model. So we have various static fields. So we have things like soil type, sea ice cover, land and sea ice cover, terrain, top of atmosphere incident solar radiance. And we also, because our architecture is sort of a hybrid of transformers and convolutional type stuff, we also have to deal with the fact that the Earth is a sphere and not flat. And we do this but doing padding. Basically, we just copy information over from one end of the globe to the other, and then for the poles, we do this kind of 180-degree flip padding so that if you're going across the constant line of longitude, you end up on the other side of the world. So that's we made sure that's all correct. It took us a few iterations to eventually get there. Not every model actually does this in the literature, but we found this is effective. So first we want to calculate how well are we actually obeying this. So one of the issues we ran into is that error 5 itself does not conserve dry air mass. So that can be a little bit of a problem. But we take the original like quarter-degree error 5, so it's not really original. It's the like slightly regretted original. And we course grain it to 1 degree to make this process easier to train. The same patterns show up at 1 degree as a quarter degree. And then we train 2 models. We have a baseline model with no physics constraints and then another model with the physics constraints. Otherwise, everything data is equal, model architectures are otherwise equal. And we find with global dry air mass, if you add in the constraint, it remains flat. It's not 0. And this is because we're running into issues with like these 32-bit floating points around GPUs. So we're not, in terms of the precision we need to get exact conservation, we're not there, but we're much improved and it's pretty stationary. Same with moisture budget conservation. You see things bounce up and down with precipitation tendencies and stuff. With the baseline model tends to drift with both precipitation and evaporation amounts as you run it out further in time. But if you're doing with the conserved model, it just bounces around consistently, and you can keep running it out. In fact, we've run both models out a whole year, and we see when you go out to that scale and look at some of these global dry air mass tendencies versus error 5, that we have much less. We managed to keep it right on the entire period. The baseline model actually does it varies a lot, but it's not like going completely off the rails necessarily. But it does have some more variation than one might expect. And you also see this in Error 5 itself actually has a fair bit of variation. But I think consistency is important if you want to maintain this over a long run to keep it from really drifting off into weird states. In terms of how this actually improve the forecast, at shorter lead times up to like 96 hours, it doesn't really seem to make much of a difference. But past 96 hours, we start seeing the models drift off in different directions, and are like in this case, our MSC difference, higher is better in this chart. We are seeing slight but significant improvements the further out you go in terms of temperature and geopotential height and mean sea level pressure. And you can see kind of the distributions of the errors, like where the errors are. A lot of the bigger differences are happening kind of around the poles, so especially in the Southern Ocean and up near the North Pole. So then one question we got during the reviews and from a lot of people who've seen this work is, why not apply the physics constraints only during inference? Why you can just slap this on there, and like that seems like you just do that really easily. And the problem is it doesn't actually work. We tried it. So we have our baseline model, the yellow line, the applying physics constraints. Basically we have like a mass constraint, and we have mass and energy. And so even just having a mass constraint gives you a big improvement in performance. Energy helps a bit more on some of the fields. But if you only apply during inference, what we find is, this to the baseline model, we actually get a significant drop in performance even over the baseline without any physics constraints. And we think it's because it's just driving the model out of its like comfort zone. It's like the state it's used to. And also you're having to do a really big shock to the model to apply this physics constraint versus if you're doing it during training, as you like, because it's back propagating those constraints through the model, you're getting a solution. Like the model should also learn smaller and smaller corrections, and by itself should give you a pretty close result even without needing to so the hammer you have to hit it with is much smaller, and so that should result in a much more robust and stable model, and that's what I think we're finding here. We also looked at things like moisture budget differences over time. One of the big, I think, areas of improvement in our model is the fact that we're able, like with the physics constraints on precipitation, we get rid of what's called a drizzle bias, where you get like really fine scale, low amounts of precip in areas that shouldn't be having precip, like the Sahara Desert or in Antarctica. And even IFS it's not as bad as in the Fushi base, but it does have some of these issues. And we're able to basically filter that out entirely. And that's where a lot of our improvement in skill over IFS is coming from. At the same time, we're not worsening performance at the extremes. We're still getting extreme precipitation and looking at that even over very long rollouts. We do get a few wave features that are showing up in the model, and that kind of show up in some of the budget sort of things. So in the physics, we sometimes see some equatorial waves, or the baseline model, we get some much bigger artifacts that start showing up later in the run. So that's still an issue we haven't completely resolved. But like we still seem to get like decent forecasts otherwise. We also wanted to look at not just precip, but like how does this affect other fields? And so one of the things we dug into is like, so this is an example case similar to the Storm Sierra and Storm Alex, but we compared Era 5, IFS, Fushi physics, and Fushi base. And what we saw was that while none of them, I say, get things exactly the same. This is a 7-day forecast, so it's a pretty challenging problem. But we're with our AI and WP models, we're able to get this like stronger jet, much better, and that it's more cut off. It's not completely cut off like in Era 5, but we're getting things more in line both in the horizontal as well as in the vertical. We have a much stronger potential energy to kinetic energy conversion with the physics-based model than with the baseline or even IFS for that matter. So that's so even though we're not explicitly messing with like some of these fields, is a very global kind of hammer we're applying to it. It does help strengthen the internal consistency of the model as well. And we didn't want to limit it, so this was all initially done on pressure level model runs, just like a lot of the other modeling approaches. So then there's a question of like the vertical coordinate system we know is very important from like doing any kind of weather or climate modeling. There's been a lot of work over the years of figuring out what's the best vertical coordinate system. And most teams have settled on this hybrid sigma pressure coordinate system that is terrain following. It has the advantage of it's always above ground. and you can relax it to pressure levels like further aloft. The downside though is some of these terrain impacts extend well beyond the let's say the boundary layer, well up into the atmosphere, or even like in Era 5, if you look at the native coordinate, you're seeing the effects up to like 200 millibars. If you're on pressure coordinates, spatially you're a lot smoother. Air tends to kind of, a lot of the equations simplify really nicely on pressure coordinates, which is why we analyze stuff on pressure coordinates for the most part. But it does run into the ground, and the way, say, Era 5 treats things below ground is sort of like it makes up numbers down there, and how it makes up the numbers depends on what variable you're looking at. So it gets kind of complicated, and some of those areas can propagate. Also, with the pressure levels being chosen, you tend to have less vertical resolution near the surface compared with the hybrid sigma pressure coordinate system. Although you could presumably sample more pressure levels. So we apply the same conservation schemes, same Fushi architecture, but change the vertical coordinate system and just to see what happens. And what we found was you got a slight improvement in precipitation when you combine both the sigma vertical coordinate and the physics constraints. If you just do the sigma coordinates without the physics constraints, it does a lot worse. So they both combine to help, and particularly at helping with drizzle bias, but also like we get some slight improvements at like high frequency structure, not by a lot. You have to kind of zoom in to see it, but it's there. And then looking at individual case studies, we also see improvements in getting more extreme precipitation over land in terms of representing the near surface structure of the winds and moisture, as well as like where the precipitation is falling. The pressure level models just don't have as much precip, or much weaker, and we're still missing some of the. It's not perfect, but we're getting like the shape better, and we're getting the intensities better in this case. It's not the be all end all, but it certainly is helping. We then wanted to take this not just from to weather scale, but let's see how far into the future we can roll this out and do all these things to apply, and does that result in better climate, better longer term projections. So instead of using Era 5, we used the community atmosphere model, trained it over 30 years, and used our Wexformer architecture, which we had developed from like kind of in our initial credit experiments, but applied the same kinds of corrections we had done to as the previous two talks. And we added extra diagnostic variables to handle this. And basically, this is all in an archive paper led by Will Chapman called Camulator. We get throughput, and this also has all 32 vertical levels, also on the sigma coordinates. So we have 480 simulated years per day, so we're about 150 times faster than CAM, which does 14 simulated years per day. So it's fast, but is it correct? It turns out, yeah, we actually, in terms of a lot of bulk things people care about, over the initial training period, yeah, we do quite well. We run different Camulator ensemble members. Basically, we get internal variability after about a couple weeks, and then the actual CAM run we trained on is a consistent member. We also did climatological SST forcing just let it roll out. Basically, I think this is for a couple hundred years. It's doing just fine. It's variability. We have in terms of our kinetic energy spectrum, potential temperature spectra, we're looking really good. There is still some smoothing, but not nearly as bad as what we were seeing with other models. And we conserve all of our budget terms and water paths. And we did a baseline version of this that doesn't do that. And while it eventually kind of converges, it doesn't have the same values. So the constraints definitely help in this case too. We trained this model only out to we did like a 6-hour time step and then a 12-hour time step with mean fields to not instantaneous. But we were able, even only training out to 12 hours, we were able to pick up on large scale teleconnections. So we have things like the Pacific North American pattern, the North American oscillation, INSO precip. All of these sort of match up closely between CAM and Camulator. If you look closely, there are some differences, but the broader scale signals are very similar. We also tried some other forcing experiments. So we added CO2 as a field to the model and trained on that, and then let it run outside of basically the initial data. But we did basically letting SST and CO2 vary as a kind of forcing scenario, but then also held one or the other constant. When you hold CO2 constant, it doesn't seem to have a big effect on the model output. But when you hold SST constant, we see basically the model stays flat, even if CO2 is increasing, but eventually the inconsistency causes it to kind of go bananas around 2048. So that means I think the model isn't capturing all the right physics and the causality structure between these two. I think some of that is because we don't have explicit aerosols and we don't have other cloud connections that we might need to add ways to handle that in the future. Sea surface temperature. So basically, ocean, usually one of the things you see with global warming is the ocean warms up. So you can sort of simulate, do pseudo global warming by just warming the oceans, even if you aren't explicitly resolving all the radiation effects of CO2. So some ongoing challenges, say process evaluation is certainly continues to be an issue, especially the degree to which AI weather models capture particular processes more systematically. I think some of the things we're talking about, maybe formal verification, maybe some of the XAI approaches might help us dig into this a bit more and be able to quantify some of this. But right now, there's still a lot of eyeball testing happening, and ideally, we need to get beyond that. There's certainly approaches that people have done and lots of scorecards and other things, but I feel like there's still more analysis work that needs to be done to really change some of the more interesting, like object-based analyses or scorecard analyses with tools to like really get into the underlying processes and how well they're being captured or not. One of the areas where we see big issues still is these fast versus slow timescale processes. So often the machine learning model, these emulators tend to overemphasize the fast processes over the slow processes, mainly because the slow ones just take longer to show a signal. And if you're training only on like next time step prediction, some of those tendencies aren't basically going to be learned. And this is especially apparent in places like the stratosphere or in the deep ocean. We're both seeing like auto models drop off in scale in both areas, both because they very slowly, but also because they're much more heavily stratified and there's this correlation between different levels. And so how do we deal with that? I have some ideas, but it's, I think it's going to be an ongoing problem for a while and a big open challenge. And some of this I think comes down to like the AI models probably are heavily biased toward handling advection really well, but they kind of underdo the convection. Arguably, that maybe it's possible that the NWP models and climate models currently have, like, we know they don't represent convection entirely correctly, and that they may be overdoing it, and that may be causing additional noise into the system. And the AI models happen to be damping that out. But they arguably are damping it out too much, especially for like the structural example I was showing earlier. So how do we solve that? Well, I think that's an interesting open question. And then the final one is learning the causal structure of force responses. So I showed the CO2 and SST example. Arguably, like there's a lot of different processes at play, but ultimately it's like some of this is more CO2 in the atmosphere drives more reabsorption of reflected light being re-emitted down in all directions, but downward into the ocean where it's the ocean heat uptake happens, and we also have more carbon going into the ocean as well. So there's a lot of processes going on in that, but how can the machine learning model learn the causal structure? Especially if like these responses to changes to CO2 and changes to SST are happening at the same time, how can it distinguish one from the other? That's a number of groups I've seen have been running into this issue, and I don't think we have a good response, but it's something that's really important so we can actually say like if we want to diagnose process like things like XAI type stuff from AI models, like answering this question is really important. So in summary, I think I want to hopefully convince you that what data you choose and what kind of post-model global physics constraints can help improve your weather forecast and not only like overall accuracy, but also some of the structural representations in the model. And these extend out not just to weather timescales, but to climate timescales. And we're finding promising results with doing atmosphere emulators, and we're starting to extend this into the ocean and looking at other parts of the Earth system and see how they all couple together. And so with that, if you have other questions after the panel, I'll be around, and here's my email, check out credit. We also have other papers you can find on our website. So with that, happy to take some questions. Thank you.
Any questions before we switch to panel?
Thanks for the very interesting talk. I was curious about, you showed for the accumulator results, sort of an ensemble that you generated. Did you notice any differences in that, like the spread of that ensemble between the, like physics constrained version and the non?
I haven't looked at that directly. I will say, like, for a lot of the models, we've been doing a lot of ensemble experiments, and one of the things we've been consistently seeing is that especially the wax former models tend to be, you have to really knock them hard to, like, they're not very sensitive to initial condition perturbations. They do eventually diverge, but in initial time steps they aren't super sensitive and tend to damp out a lot of force noise. Adding noise into the latent space helps a lot, and we can calibrate that, and we're working on some results with that right now. But yeah, to answer, I don't have a good answer for you. We haven't looked at that. I think it would be a good thing to look at to see if this has other knock-on effects. Using an ensemble loss like CRPS, like multiple groups have now done this, and we're finding that it helps both ensemble diversity, you get a calibrated model, but also you're able, like, the models are actually resolving some of the finer scale structures better in their data. So there's also something to, like, one model to train on MSE losses, and that damps out some of the finer scale signals as well.
Thank you.
Any other questions? I guess we're ready to switch to panel line.
Panel time. Yeah. All right, so the way this will work is, I think we'll all sit here and move this chairs to the wall. Yeah. And so we're not sitting close to each other. So I gave the panel member one question in advance that I have only about 10 minutes to think about. And the way our format will be is I will ask this first round of questions, then take the privilege to ask one first question and then open it up to everyone and just be the moderator for your questions. So the question I'm going to ask everyone in the panel is, what's one thing that you found really interesting or surprising in the two other talks? Then you have the people to ask the question to. So maybe we'll start with the very first speaker here.
Okay, so from Antonio's talk, I actually learned a couple of things. So the benchmark is very important for evaluating explainability methods. And then we all learned that this R-square is now really good way to evaluate those methods. And the way to go is ensemble approach for the evaluation of usability of those methods. So yeah, that's very interesting. And from David's talk, first of all, I'm not an expert in this area at all, but I still learned that this credit, so the community research or digital intelligence twin project, I think it's a very impressive project where we can upload data and train and deploy the models. And I believe it's funded by NSF and the government. So I think it's a really, really exciting project to on I1.
Is it still funded, David?
Yes. Okay. Still funded. That's why I'm sitting in this room right now. Otherwise, but yeah, it's a lot of NSF-based funding plus I would say AI2ES was part of it. Schmidt Sciences through the M-Squared Alliance project help contribute to it. We've also gotten some funding indirectly through Google because they bought a weather company that NCAR had ownership rights in. Some of the money from that sale has funded people in the research applications lab on doing some regional weather modeling. So we kind of have funding from, it's like indirectly from some of the private sources too.
So just curious, like how much like annual compute budget do you get for the project?
Our lab allocation, I think, is around 300,000-ish core like GPU hours.
Wow.
And then we've also gotten some special allocations that are also in that neighborhood of 200,000 GPU hours. And then we've also been leveraging other labs allocations for work going on in those labs because they also want to. Some of the weather and climate models aren't ready for like like, there's been a lot of work done by folks, some of the folks in this room even on porting models, the weather climate models, GPU. Some of those are progressive varying rates, and the GPUs for traditional modeling are still being underused at NCAR, so people are happy to throw their compute at the AI models for now. So we train like these models are showing. It's like you can train on, like, for a 1 degree model on 32 GPUs, it takes about 3 days or so. So it's not, it's a bit of work, but not terrible. For once you get to the 1/4 degree, it's like 3 weeks. So that's much, that starts being a much bigger effort to shepherd that through.
I'll translate that to discreetly stealing core hours from other groups.
Yes.
It's very good at it. We used to work in the same group, so here we go. All right, with that, I'll switch to you, Antonius.
Thank you. Yeah, I have to say, very exciting. And I was already expecting that this meeting would be very exciting. So that's amazing. From Soonho's talk, I learned a lot. Two fascinating talks, both of you. I learned about Lean. I learned about, and it's fascinating to me as a concept that we have an AI that is an assistant essentially to mathematicians for proving theorems. That's fascinating to me. But I did have, what made the most impression from your talk was this slide that you had. You were very nicely summarizing that, you know, language models are not good agents, at least as of now, when it comes to reasoning and checking our reasoning. Then you correctly also highlighted that sometimes humans ourselves, we are not very good at checking other humans, especially when it comes to knowledge that is at the very forefront of when we were pushing the boundaries of human knowledge. We are not ourselves very good judges of what other humans are doing, which is fascinating to me. And then, but then Lean can do that, or it seemed from your talk that the idea is that Lean can help with that.
Yeah.
And to me, that's mind blowing. And I had the very simple questions, and you don't need to get to that now, but it is in my mind. So what is it that Lean can do better, even than the greatest human minds that can help with this at the pushing the human knowledge, the boundary of human knowledge? You had a slide, and that was very informative as well, where you mentioned that this great mathematician was saying one of the things that Lean can do better than humans is that it can have all the concepts of the proof in its RAM, and humans run out of RAM essentially.
Yeah.
And that's informative. I get that, but I would love to hear from you if you have further insights about why Lean can help push the boundaries of human knowledge better than some humans ourselves. And I don't know how I can get to.
No,
Yeah.
I think that's a good.
Okay.
Yeah.
I mean, first of all, Lean is a great grader. So given a theorem statement and a candidate proof, you can mechanically check whether the proof is correct or not. But does it actually generate a new theorem statement or new knowledge? Actually, that's not the case. So that's why we still need a human mathematician or AI who can come up with a new insight or a new statement or meaningful statement or problem to work on. And then they can still use Lean, and they can still prove theorem by themselves manually, or they can use AI to come up with a proof. But still the role of the Lean in the whole picture is just as a mechanical grader. But it doesn't sleep, it doesn't complain, and as long as we have many CPUs, we can parallelize them. So that allows us to do like scale in this picture, but that's kind of the role of the Lean.
But it's not, so it's not as an authority per se, meaning if there is a proof and a mathematician says, I think that proof is correct. We are talking about a very complicated theory now, really at the very forefront of human knowledge. But Lean says, no, it's not correct.
Yeah.
in that case, do we look at it again, or we'll say, oh, it's an AI, we don't trust it?
So I mean, this has something to do with the explainability,
Right.
which
Okay.
is one of your interests. So when Lean says this proof is incorrect, it just doesn't just say this is incorrect. It actually gives
The
you
reason.
the line, just like you
Right.
compile a C+ program,
Right.
and if there is a bug or error,
Right.
it actually gives you the line number and some explanation why this line is incorrect. Lean gives you the same information, so you can actually debug it from there
Okay. So it's like a debugger for proofs.
for mathematics.
Okay.
Yeah.
That's amazing. Okay.
So again, I mean, for computer scientists, people who are using program for their life, this is actually not something very novel. But if I go outside of the CS community, people take it very, very interesting and novel. So
Right.
that's my experience.
I belong in the second. And then for DJ's talk, I'm still fascinated by the fact that we can now train emulators, AI emulators, that are essentially data-driven models that simulate climate, the weather system. And it's fascinating to me. Why? Because this means that determinism, that we already knew that determinism exists in the data. And we don't necessarily need equations to represent that determinism. Of course, we can do that. But these AI emulators recover this determinism from the data. In some cases, outperform the models that are based on the equations. That to me is fascinating to think about. But specifically when it comes to cumulator, have you noticed, are there ways are there conditions that once you start implementing in the training of cumulator or other AI weather systems, then the AI system already accounts for other conditions, so some conditions become redundant? Are there laws that beyond a certain point, then AI is learning and it doesn't need for those laws to be prescribed?
Yeah, I'll say we haven't, the one test we haven't done in terms of these ablations is turning, like having, we usually start without the constraints on and let it like kind of learn the base system first, and then we turn the constraints on. Sometimes having too many constraints early on means when you have like a very uninformative prior, basically just random noise for your weights, the model actually doesn't converge. But if you can get it into like a decent part, like on the like kind of in the vicinity of the manifold, then putting on the extra constraints can help it go into a more, say, physically, it's a regularization in some ways. Get it on a physically constrained part of the manifold, and that does seem to help just to an extent. And like this sort of lines up with some of the stuff that like Tom Buechler had been working on with some much simpler models a few years ago, where he also found that soft constraints, which is a popular way to do this, they kind of help, but they don't preserve the constraint, and so the models can still go wild. But hard constraints, the models can still learn from them and get a more robust result. So I think there's still biases we see. Like one of the things we see during training is that between from epoch to epoch, so like from like kind of one pass through the data to the next pass, sometimes the model will shift from focusing on kind of more weather-like features to more climate-like features, and so we don't actually get a straight convergence. It's more of it starts circling some like global minimum, but we don't, but it's still struggling to find that. And so there's, I think, more room for we saved a bunch of the time, the stopping points, but there's more to explore. I think limiting factor is the people's eyes and with climate expertise to actually look at the stuff in more detail.
So the more constraints one can implement, the better. There is no saturation when it comes to.
I think the order matters to some extent, and if you over constrain that, like, because you still need to have the MSE loss or CRPS loss.
Right.
If you only use constraints, basically the model just doesn't predict anything. Right. It's like, oh, it just doesn't change. That preserves all your constraints.
Right.
All right. Your turn.
Yeah, so for Soonho, sorry, yeah, so I was like, yeah, so for Soonho's talk, I hadn't really heard of lean before this. I follow like the newsletter of one person who's in like the say software verification community and tends to be a pretty prolific writer, although I'm blanking on his name right now. But he was talking about lean. I didn't realize he was talking about this particular software. So I thought he was talking about like Lean Six Sigma.
Yeah.
But that said, it's a really fascinating software, and I think there's some like interconnections between like sort of the use case for the emulator stuff I'm doing and the like mathematical proof work you're doing and working with others on, especially around just like when you have an orders of magnitude speed up and being able to validate something that changes the way you can interact with the system. Like there's things you're thinking about doing with AI models that are these emulators that you couldn't, like in terms of ensemble generation or steering or other stuff that you couldn't do with a traditional WP model that takes a giant supercomputer and hours to run. So I'm wondering, I guess the question back at you is like I think the CS Lib looks really exciting, but where do you see this? Like, how might this change? Otherwise, how might this change ways people do math, like advanced mathematics?
I think it's already changing advanced mathematics. So more and more people are using Lean nowadays, and there is a journal now, it accepts formal proofs. So, I mean, in computer science, actually, there are many conferences nowadays accept artifact. So when you submit a paper, you need to submit not just the PDF, but also your program or software. And there's a separate committee evaluating the quality of the artifact in addition to the paper. So I think in the future, the role of the math reviewer, for now, it takes actually like more than 2 years, 3 years. If you submit your work to a journal, it takes 2 to 3 years to get the review. So the cycle is very slow. And partly it's because human reviewers, they have to review the work like from top to bottom. And the future that I'm envisioning is the gory detail will be proved in Lean, so that the math paper include the Lean proofs, but there should still be the human natural language PDF, because that should talk about the value of this work, like the beauty of the work, why this theorem is important, what's the implication, what's the aesthetics of it, that kind of what's the meaning of it. Like, I think that's the role of human in the world of AI. So and it's not just like math. I mean, in most of the STEM science field, maybe not within my lifetime, but maybe within like 200, 300 years, anything formalizable can be formalized in the future, and that can be really accelerated. So that's kind of my view.
And then for Antonio, I've seen a lot of your work from your postdoc. So I was really excited to see the new like where you're taking it in this new benchmark and looking at kind of what's the effect of both the data, the amount of data versus the amount of noise, and that the result was done. It wasn't entirely intuitive, which is a really cool result, and it also helped validate some of the things I kind of seen sort of empirically, but didn't really have a good way to benchmark. So I think you have a benchmark that could now be
functionality. I think that'd be maybe a discussion to have with like the early stage developers, either maybe coordinating with DJ and the credit team, and like maybe some way they're thinking about and planning to model that how that user community is for.
Thank you. I'm glad my work is being talked about. Glad the room. But yeah, I guess like during the break we talked about like kind of where you're going next with it. So like where do you think some of the, I guess where do you want to go next with this kind of validation? Where do you see as the big challenges like that are still facing the XAI community, and how we can use this more and for like helping with different kinds of analysis tools?
Yeah, absolutely. Yeah, thank you. Many challenges in the XAI field. The first challenge is this. The core challenge is that it cannot be falsifiable. That's the first one. And we are trying to work around this thing, and that's why all these other issues
emerge. The second is this high inter-method variability that I mentioned, and this benchmark can be helpful, or other benchmarks. By the way, in the computer science literature, there are new benchmarks that refer exactly to the XAI. So they are XAI benchmarks, where there is a ground truth of the explanation, and you can benchmark different methods, different training settings, different models, and so forth. But the very important challenge, and we are getting here now to the causality that you also highlighted in your talk, is that the XAI is used to explain the model. So it's explaining what the model has learned. It's not necessarily the system. If the model has learned spurious relationships about the system that helps the model predict and achieve minimize its loss function, this is what the XAI will solve. In other words, all of us have been students. You know, there was this course that the professor would have a quiz, and we could answer the quiz, multiple choices, based on how long the answer was. And we were getting maybe, I don't know, 7% score. This is spurious correlation. We were exploiting the correlation of the long answer with the correct answer, right? So an AI model can do that, can cheat, can find out spurious correlations in the system and arrive at the correct prediction. If you explain that model, you are getting the spurious truth. It's not the real system. So I want to go somewhere where we can look into, and that's why eventually these results I showed have to do with structuring the consensus. It's not consensus per se, it's the structure in the consensus of different XAI methods. Because it seems from these results, it seems that if there is structure in this consensus, it's more likely that the model has learned something physical and not spurious. Now, when it comes to next steps, I would say I need to try different training settings, and we talked about that during the break, meaning, for example, could a model that is trained with physical constraints imposed deal with the issue of noise? Maybe a model, even if it is trained on data that is noisy, if it is constrained physically, it learns something physical, much better than an unconstrained model does. So different training settings. I want to try cases where I give the input to the model is incomplete, meaning in some cases in Earth system applications, we don't have all the predictors we would want to have. Like we use SST to predict another variable, but maybe there is another variable that we ignore that drives the variability in the target variable. So in some cases, we have a limited number of predictors. What happens in that case? Now that we have a controlled benchmark and we can test all these hypotheses. So different trainings, different assess different limitations that mirror climate applications. This is where I want to go. But the ultimate aim, I believe, is to come up with techniques, or not techniques, I would say best practices, so that users can be more certain, not absolutely certain, but at least a little bit more certain that the model is learning something physical rather than cheating, right? This is where I would like to go. And I think that I could, I should learn from you too. I should read the papers in that part of the literature, because it could be a great inspiration for the application side. I realize that a data-driven model is not the same as a language model or a reasoning AI, but there might be parallels, similar situations that we can learn from what is being done in a different field. Yeah.
All right. Well, so your last explanation is a perfect transition, coincidentally, to my question. As I'm a statistics professor and used to work here at NCAR for a long time, I think many of you know me. So what I've been thinking a lot about is how can we use more traditional statistical models in conjunction with explainable AI? Because a traditional statistical model is by definition explainable because you pre-specify the features basically and say, this is what we will use to explain what's going on. So I'm going to use the example from your bird because I think anyone can relate to that. So statisticians will approach it and say, let's talk to an expert. The expert thinks about, we want to know the overall size of the bird and what the color of the eye ring is and what the belly stripe looks like. So that's how we would think about this. And we would say, well, given we can measure these features with some error, like now we run our random tree model or whatever it might be in detail, that model, and come up with a classification. And some work I've been doing with Allison in the compression setting is to think about now could we use explainable AI to come up with more features that we didn't think about, and maybe all the bird experts didn't think about. In reality, it's like the tail, how it angles, so making obviously this totally up. I'd love to get your thoughts on that, because to me, it seems like there's a lot of room to use this more usefully in conjunction, because once you have these pre-specified features, then you can test this in all kinds of scenarios where you can say, now I'm imposing this, assuming these are indeed the relevant features, and see how well that holds up in many other settings. So that's my question. Both of you others can answer that as well. But I'll start with you. I'm sorry.
I can say that this as an idea holds great potential, and I think I have seen in the literature, in the AI literature actually, people using LRP. LRP is another XAI attribution method. To train the model, meaning they start with initial weights for the model, and they apply, they predict, and then they use XAI to figure out the explanation, and then they pose constraints on the explanation. And this is they build up a loss function that has to do with the explanation, and they have the loss function that has to do with the prediction, the loss function that has to do with the explanation, and they try to minimize both at the same time. So it's like training a prediction model, but imposing constraints or a loss function that has to do with the post-prediction reasoning of that model, which is essentially what you are describing, applying XAI in a post-prediction setting to figure out features or explanations that we didn't think of, and then update this model with this feedback. And I think it holds great potential because it's happening to some degree, this combining the explanation and the prediction loss to train already within the training algorithm. And so, yeah, the only thing that I can mention I have to say to that is that, yeah, it holds great potential.
So that's a way to build like self-improving AI system, right?
Yeah.
But then it's more and more important to come up with the right explanation,
Right.
because if we come up with the wrong explanation, then
Absolutely.
it's going to deteriorate the quality
Absolutely.
of AI, right? So.
But that's why I cannot see the statistical model, because in the statistical model, because we impose it, yeah, we kind of have to have the right explanation. Like we're predefining the explanation, and seeing how well that holds up using AI tools.
Right, but then when you get the explanation after you apply the XAI, and that explanation could be a potential new feature to the model.
Exactly, yeah.
That new feature we would want to be as reliable as possible, meaning the explanation should be something that relates to the system.
Correct.
That we haven't thought.
Statisticians, the way we would think about that is we would test that new feature in new settings.
Yeah.
We don't do that optimization framework. It's just a different way of thinking about the world.
Right.
If you tell me now that tail is really important, I would say, well, let's try it out.
Let's try it.
And you imagine we have, is the tail really important?
Yeah, to kind of build on this, I think this debate has been going on between statistics and AI for decades now. For those who haven't read it, I would say there's a seminal paper called Statistical Modeling the Two Cultures by Leo Breiman. Look it up. It's a really good paper. Leo Breiman is also the kind of creator of random forests, which is a very now still extremely popular ML method for tabular data. And kind of the underlying, I think, debate, at least as he posted in the paper, it's between
like framing the problem in terms of like, let's pick a data generating distribution and versus like, let's focus on whatever maximizes prediction accuracy on a test set. Because he found in his experience, like trying to actually assume everything a priori usually got poor predictive accuracy, but then using something like a random forest, which makes very little assumptions about the data, but then gives you a highly accurate prediction, tended to work better in a lot of his more applied situations. And so he was kind of leaning on that side, but I think there were a couple of responses in the paper from other mathematicians. But I think what's happened is both fields have kind of intermixed a bit more and learned from each other. We're looking at like making assumptions about how your data is coming from, and not just that everything is IID and uncorrelated. Either through, there's a lot of different ways to do it, whether it's through like like how you set up your neural network architecture and use convolutions or transformers or LSTMs or whatever, or you can use more traditional linear algebra kind of techniques that like and have covariance matrices and assume a just like over predicting on a we want to have an output that looks like a Gaussian in terms of its predictive error. Let's predict the parameters of a Gaussian distribution and optimize negative log likelihood. That's all kind of statistical sorts of optimizations. And then there's also I think getting back to Dorit's point about like we can assume features. Like where deep learning was kind of a big deal is like we didn't have to assume as many features, and then we got like a giant improvement in performance. But since then, there's I would say a lot of the big AI approaches are great at searching the space, but they often have a lot. They're extremely inefficient, and we're starting to kind of pay the price for this literally with all these data centers. But often there's ways with XAI and with other low rank augmentation type approaches where you can like figure out what is the actual key features that are being learned by the model, and then come up with a much simpler way to do that can be easy to reason upon or to enforce. So you're not having to do all this excess calculation that isn't really going anywhere other than filling up your GPU and cloud bill.
Right. That Breiman paper, by the way, I used to think my graduate level data science courses with half CS and half math students, and it's always fun if the people like this paper was written before I was born, but then they still like it. It's kind of amazing how well that paper holds up. Actually, I did not know you like this paper.
Yeah, it's one of my favorites.
Good. Well,
What was the name of it again?
Statistical modeling the two cultures.
so Breiman is the kind of interesting side study. I think he was at Berkeley, a really theoretical, very theoretical probability person, but then really branched out. Yeah, so he had the full grad in the like people in the stat community really thought like, what happened to that guy? Yeah, and I think he has changed the color, and I just started some useful things. All right, with that, I'm opening up to the audience. Who has questions?
There's one out there.
Oh.
You want to read it?
Let's see. Yeah, I could take a stab at that question. So I think the heart of it is in traditional models, you can turn on and off different processes and diagnostics to kind of get at the causal mechanisms. And how would you do this in emulation space? So let's say one way we can do it if you don't want to mess with your model is like kind of using basic XAI techniques. So going back to Breiman again, there's a thing called permutation variable importance, where you destroy the information content of a particular input by shuffling it. So you basically, let's say I'll replace today's temperature field with a temperature field from 20 years ago, and then put it into the model, and you can then run it forward and see how the prediction changes. And if it was an important feature that doing that transform should roll up make your forecast a lot worse, and if it's not important, it should basically the forecast should basically stay the same. And we've occasionally done this by accident. We ran into some model training exercises. We're halfway through. We noticed that we had all the the terrain height of the land sea mask upside down, the model still actually learned, just kind of learned to ignore those fields because they didn't line up. But then when you change it back, like because it learned to ignore them, changing the terrain didn't actually affect the model all that much. So that there's a the models do kind of like having it predict a future time set does introduce some level of causality learning into the process. It's still a lot of correlational stuff, but because it has to have this dynamics as part of the prediction that does help act as a guide to steer it toward these features. I would say that we can also like train different models with like a blade, take out different inputs and see what happens. And the community has kind of implicitly done this. So one of the wild things still is that we can get decent performance even without missing kind of critical forcing mechanisms and not having all the levels of the atmosphere in these models, and they can still pick up on a lot of the signal. So that's still an area that like, seems like it shouldn't work, but it does somehow. But it just that's where the failure modes become very interesting, because that usually much better than looking at the mean squared error, seeing where it breaks, where those edge cases are, really tells you about where the robustness is failing, where maybe we actually do need these fields, especially if it's in a like high impact sort of situation.
So as a traditional NWP developer, like that energy spectra sort of scares me. And I was wondering, like, how do you foresee like traditional NWP coexisting with the newer models?
So I think this is a question that is coming up a lot because it has, like, everyone's trying to figure out their compute and research budgets and focus areas for the next 5 years. I do think that there's a lot of value in the emulators. I also think there's still a lot of value in the NWP and climate models because of the fact that you can turn on and off different things and understand this, that like you have the equations explicitly coded in. So like at the very least, there's the like we want to keep our current systems as at least reference model implementations and like maybe especially improving the modularity of them and the readability, so that if we like wanted to say rewrite, take like parts of CESM and rewrite them in your favorite Python deep learning framework and test that out, that you have something you can still go back to that has a decades of rigorous validation that's been put into it. That's it. I may also see a future where we start bringing in more of the physical components and diagnostics and other stuff. And maybe there are ideas for new die cores that can take advantage of some of the things we're finding with the emulators, like this multi-scale aspect. Having only a local stencil does seem to be a limiting factor at high res, and the multi-resolution models that the AI systems kind of do does seem to, I feel like, is one of the reasons why they work as well as they do. So is there an analog to that we could simplify and put into like a more, like, can you have a multi-scale die core that could operate at different scales and then like kind of add everything up? That could have some interesting implications if we could get it to work and don't necessarily, and then not have to train it from scratch.
Other questions here? Yeah, you want to go?
This is a little bit of a specific question regarding lean. Yesterday we were hearing about Z3. And as somebody who's like not really familiar with these formal verification methods, at a high level, how does lean build on? It seems like Z3 came earlier, and then I guess part of maybe especially relevant to developers in this space is like maybe the ability to translate one's own functions into a formal language to be tested in that way. If you have any thoughts about the process of doing that for...
Let me answer first. So in formal, there are basically two schools. One is automated theorem proving. Another is interactive theorem proving. Okay. So the philosophy of automated theorem proving, the emphasis is on automated. So the philosophy is, let's focus on the fragment of logic where we can have automation. So the great example is Boolean satisfiability. So set problem. So you can have Boolean variable X, Y, Z, and you can have conjunction and disjunct and or negation, and you can form a tree. And the question is, can I find an assignment to X, Y, and Z that satisfy the whole tree, true or false? Right? This is a very famous, the first MP complete problem, Boolean satisfiability. So the problem is satisfiable, it's just MP. So there is a class of software called like set or Boolean set solvers out there. Even if the worst case time complexity is MP, but practically thanks to all the engineering that the community has devoted into, nowadays they can handle like 100,000 variable problems within like an hour. Okay? So, and the next layer is SMT server that some of us learned yesterday. So G3 is a great example. So still, the Boolean logic is too boring. Like you can only describe true or false variables. That's too boring. So why don't we can we have integer variable? Can we have real variable? Can we have string variable? And so the answer is yes. So basically we grow this expressibility from Boolean logic to first order logic. But there's certain limitation because if you allow the whole first order logic, the logic is not decidable, meaning you cannot implement an automated decision procedure for that. So if you study G3, they actually support linear arithmetic, linear integer arithmetic, linear real arithmetic, and you can also do non-linear real arithmetic, but you cannot use like sine cosine. Because once you have sine cosine, the whole theory goes undecidable, and you cannot have automation. So this is a very brief explanation of automated theorem proving. So the philosophy is we want automation. So I'm willing to sacrifice the expressibility part. Okay, interactive theorem proving. Lean is a great example. So the logic is beyond the first order logic, what we call dependent type theory. So it's very, very expressive. So actually you can write any math knowledge in this logic. So it's very nice in terms of expressibility, but the downside is, in theory, you cannot have full automation here. So that's why this is proof assistant. It cannot be fully mechanized. So you need to work with human, or you need to work with different entities. Okay. So the trade-off here is you have better expressibility, but the downside is you cannot really enjoy full proof automation. You need to do something manually, or you need to do search. You need to try this and that. Okay. And so that's kind of the answer between G3 and Lean, where the two tools belong. And your second question is about how can I translate my function into G3 or Lean so that I can enjoy the benefit of verification, right? And the answer is, for certain languages, actually, there are some tools out there that can handle that kind of translation. But again, we have the same problem because, like in Python or C++, the expressibility is too incomplete, right? You can write almost anything, but most of them cannot be handled by G3. So even if you translate things into first order logic, G3 cannot handle for some cases. So, but if you can translate them into Lean, the translation can be more straightforward because expressibility is better, but you don't have the full automation at the end. So traditionally, so all the technologies that I talked about today, and also all the techniques that you learned yesterday, they have been available for like 20, 30 years. But the human adoption has been the most challenging part. Like, if to be honest, like if I teach like a functional programming language, Haskell or OCaml, not to mention Lean, to like 100 sample programmers, like most of them will just give up because it's kind of too difficult. The learning curve is steep, I have to admit, right? But now my hope is AI will change the picture, right? AI will either help human to do this kind of difficult tasks more easily, or they just replace the human. So humans do not need to do this. AI will do that. There will be two directions, but yeah, like maybe I should stop here.
Did that answer your question, Theo?
So probably more questions, follow up. Yeah, but I guess just like not being super familiar with these like methods, that is helpful, yeah. To place them in that.
Good question. How long do we have?
Until 12:30.
Oh,
20
good.
minutes.
So we have plenty of that. All right. There
So lean is a language. And so, which means there's gotta be bugs because humans make bugs. And so, how does that look like with the verification language?
Yeah, this is a great question. So the question is basically, who's going to watch the Watchmen? How can I trust you? I mean,
Yeah.
I'm using lean because I cannot trust anybody else. So now you're asking me to trust you, right? That's the kind of question.
Yeah.
So, just like anything, like mathematics, they do have axioms. So lean also has the foundation axiom that you need to trust, but they are very limited. And another thing is in lean, you can, given a lean, high-level lean program, it's going to be compiled down into what we call type term. And the correctness guarantee hinges on the correctness of type checker. So basically the whole logic is, as long as type checker says this type checks, we think this is true. So the question boils down, how can I trust the implementation of type checker, right?
Yeah.
So the first answer is, lean itself is more than 200, 300 lines of code, just like any other program. But the type checker part is less than 10K lines of code. So if you really want to trust it, you just need to review the type checking part. So that's answer one.
Right.
Answer two is, there are actually independent type checkers out there. So lean type checker is written in C++ actually, but people have written lean type checker in Rust and lean itself and other languages. So if I'm really, really paranoid, what I need to do is first compile down everything into this low-level implementation, and then I send it to 5 different type checkers. And as long as everyone agree that this is correct type checked program, then I trust it. But still, there is a slim chance that every single of them has bug, even if they are implemented by different people, written in different languages. It's theoretically possible there is a common bug, and
Sure, yeah.
but we believe the chance is very slim here.
Okay, that makes sense. Yeah, interesting, cool.
And actually, I have you on my radar, but I'll quickly take one of these questions here. So Carolyn from the panel has a really good question here. Do any of the panelists have musings they would like to share about AI reasoning about our Earth system model codes? You touched briefly on the optimization piece, but I'm also thinking about things like suggesting an alternative boundary between components, lies, new coupling approaches, or exposing emergent dynamics, maybe for an as yet unsettled part of the state space. I think I'll start with maybe teacher on that.
Yeah, I'll think about a couple pieces on this. One, yeah, we are definitely thinking about the like, how do you actually, if you have different Earth system component emulators, or even an Earth system, an emulator component and a physics-based component, what is the most effective way to couple them together? There's a paper recently, the Samudra ACE, where the ACE climate model from AI2 and the Samudra ocean model, ACE atmosphere model and Samudra ocean model, where they did a coupling together. And the way they did that was they trained each independently, and then kind of trained like the ocean first, like basically keeping the they like held one. They froze one and trained the other while coupled, and then they let both vary together while coupled, and were able to get some good results that look very promising. There were some sensitivities they exposed about, like they both had to be on exactly the same grid. So like regridding is kind of a big thing of what couplers do, and currently we use a lot of linear regridding methods, but is that the best way to do that? I mean, they have some nice properties and they're fast to run, which is really important because you have to do this a whole bunch of times, but potentially you could optimize at that coupling level, and come up with other ways to to like aggregate data from one Earth system piece to another if you can theoretically optimize through that with appropriate constraints and losses. I'm also I have a postdoc, Da Fan, who's been working on also how to train AI, basically using AI models to look at ensembles of climate model output, where like you have a control ensemble that has all the standard, like you vary some of the parameters and the parameterizations and let them run it out. But then you like say add an AI emulator component, or you change something else about the model. Say you like have CESM2 versus CESM3. You run both models out. You train the model on using a method called contrastive learning, where the goal is to say, well, I don't know what the exact answer is, but these samples are more similar to each other than these two samples. So your latent space should the distances in latent space should get smaller for these samples and further apart for these samples. And actually, once we set up the problem right, it actually worked really well, and we're able to pick out, like through using integrated gradients XII method, we can backprop from the latent space. You even see clear differences in like a PCA lower dimensional representation of the latent space. We can also backprop from the latent space into state space and see where are those differences coming up. Where's the model focusing on to make these differences? And if you have your observations in the same kind of format, you can also compare against observations, and we're doing that as well. But climatologically, you could also do this with weather models. So there's a lot of cool things by going back and forth through the neural networks that you might be able to get more insights and then dig into more traditional methods to help you with the search, and then your interactive visualization comes in to start understanding why this is different and proposing new experiments to new ways to look at the data, potentially with other AI tools to help with that.
Yeah, I can add a little bit to that. I think I want to really emphasize the importance of the latent space. Many AI state-of-the-art architectures or models like the diffusion models have been shown to be very effective when they are trained in the latent space. So, and actually there are papers out there, recent papers that show they can quantify uncertainty better and faster. But when it comes to AI reasoning for the Earth system, that probably could be that we can have lean for climate, meaning the climate is also controlled and determined by physical laws, and those could be the axioms. I don't know, and work our way through predictions or projections based on, and we have a grader for a reasoning model for climate.
So I'm not an expert on the Earth system model code, but I'm also nowadays thinking about like general code reasoning from AI. So how many of you heard the terminology vibe coding nowadays? And how many of you actually tried that? Okay, like 20-30%. So vibe coding is basically you ask AI, LLM, ChatGPT, Claude, whatever model to implement certain things, and then AI will implement the code for you, and you just use it. And surprisingly, they are sometimes very, very good. Like if you want to visualize, given a data, I want to plot this chart. Nowadays, actually, I'm not like programming METplus by myself. I'm just using Claude or whatever model to do this for me. But if you think about it, this is not okay in general. Maybe if you write like our system model, you might not like use vibe coding. But who knows? I mean, the future generation, the current generation, the younger generation, they are kind of started using vibe coding, and sooner or later it can be a problem. So I think again in the future we will. I mean, the notion of spec-driven development. How many of you heard about this terminology, by the way? Spec-driven development. So the idea is before you implement your function, you first think about specification and requirements, and then you implement your function to make, and then the idea is you have to make sure your implementation satisfies the specification, right? So this is old idea. It's the basis of software engineering, what we call, right? But I think the idea will be and is now getting revived thanks to AI. So the feature that I'm envisioning is basically, we first write down specification. And if you use a good language like Lean, you can actually check whether the generated code can satisfy the specification or not. So if the full vision is fully implemented, you don't actually need to even take a look at the generated code. You just make sure the specification is right. The specification is the thing that you want to have. Then as long as the checker says, oh, your code matches the specification, okay, then let's go. Let's deploy. That's kind of the way to go. And I think it will happen soon. That's my bet.
Hopefully those specifications are sufficient and
yeah, so that's again the role of
necessary,
human programmers. Just like the role of human mathematician is to come up with the meaningful conjecture to be proved. Like
So yeah, kind of a follow-up on this thread. Is there anything in the formal verification landscape that is thinking about how you deal with emergent phenomena? Because one of the things, reason why we run these giant climate models and don't just look at the Navier-Stokes equations is because we want, from these equations, we can generate hurricanes and storms and very monsoons and various other shifts that happen across lots of scales that aren't there isn't a monsoon or hurricane function in the code. It's only something that shows up, or we have an issue in CESM where sometimes the library or C just freezes after hundreds of years of running the model. Are there anything in the formal verification space that can get at, or anyone thinking about how would you check in that, check for that kind of stuff? Or is that well beyond the scope of what formal verification is trying to do?
Yeah, I mean, I think it's difficult to find analogous concept in formal verification. Yeah, so maybe we are not there yet, to be frank.
so could that be a blind spot in this domain? Because as DJ is mentioning in the climate, there are things that will be happening because the system is non-stationary and we are forcing it in certain ways that we haven't observed yet. And so statistics or specification or verifications that we can come up with maybe are not representative enough of the future climate system that we haven't seen yet.
Yeah. So I think in programming concept, basically everything boils down to specification. So if you have kind of loosely specified specification and then provide it to AI to generate a code, then AI is actually very, very good at finding a loophole. I think you also talked about it, right? So it's going to come up with a very interesting, funny case, but it actually satisfies all the spec that I enumerated. But when you look at it, you can tell this is not what you wanted, right? So again and again, the mining specification, learn what you actually need to have. That's kind of the art. And that's actually the most difficult part, in my opinion. So in our area, there is a technique, a process called auto-formalization. So the idea is, given natural language, we have to come up with formal equivalent. And the most difficult part is natural language descriptions are almost always very ambiguous. And the wisdom that we learn is most of the time, people do not know what they really want. Or they haven't really thought about it in a deep way. So this is very, very difficult problem. And I think, this will not be solved because it's about capturing human intent, which cannot be solved perfectly, right? So I think that's one of the great areas to work on as a human.
It may also be the inner, you mentioned this interactive proofing kind of approach. That seems like it might be a way to get at some of these, because in a way that also creates an emergent phenomenon of this proof by challenging the human and the human challenges the computer and back and forth. That maybe that's the pathway to some of this is I don't know what I'm going to look for, but I know I want to see something that looks like a blob of some sort. That can we formalize that and then I'll try something and that gets that, but not exactly.
We are better at knowing what we don't want.
Yeah, exactly. So kind of related, there are also people working on scientific discovery using AI, and they are talking about, we're gonna build the system and given a idea, it's going to design experiment, run experiment, to try different hypotheses, and at the end, it's going to come up with a Nature publication, for example. Then many people emphasize it's really important to design such a system in a way that we can steer the direction of the research. And it's actually very challenging because, like, in one extreme, AI can just do something for like 3 months and come back with a Nature paper that they believe, but you can tell that's not what you wanted. So, but in another extreme, you really want to work with AI like every minute, every 5 minutes, but that's not what you want, right? So you need to hit the right sweet spot and how to steer the AI who doesn't speak a human language. That's kind of very interesting and challenging topic nowadays.
With Ganesh, and then we want to get to your question.
Yeah. So I read a lot and it's very fascinating. So I'll start with my original question, which I had to add a few things because some of it was answered. Yeah, I think AI systems ought to be doing concept synthesis. This is what Sanjeev Arora says. There's a talk by him called Parrots No More. It's a really nice pithy talk because he actually measures the degree of difficulty of a problem and how many concepts are involved in solving it. I suspect this is what is going on in material discovery and drug discovery because it cannot be monkeys on a keyboard because it must be figuring out some laws of physics that informs the system. So maybe you will write a paper, Soonho, saying graders no more, one day. It's beyond that. And Terence Tao says some observations where he got insights into some of the proofs that he's doing, But there could be limits to that. So two things I can throw out is brute forcing. This was a question raised in the Z3 SMT area. That's one automation approach, but even their concepts synthesis ought to be involved. So if you look at the chromatic Pythagorean theorem by a person at CMU.
Yeah, Baramashetru.
Yeah, it's a terabyte of proof, but I don't think that was brute forced. I suspect there are still concepts fed into the SAT search space. So I suspect anything is modulo these concepts that are overarching and generalization modulo these concepts ought to be happening. And just to address the other things that came up, my student who is at NVIDIA Research, he recently gave a talk to my class saying, how do I use cursor in my organization? You have to write a lot of rules to guide cursor to synthesize useful code.
By the way, cursor is one like editor doing vibe coding.
Yeah. So in the sense, it's not Vibe anymore. It is a lot of intent express. So finally, there's some meta level specification. Otherwise, it's useless. So that's a tangential thing. But I think what I was going to say is, you can predict a material, then synthesize in the lab and see if it is good, and then publish in Nature. So the analog of that might happen in theorem proving. Why not?
Yeah, sure.
I don't know. What's your opinion? I'll go for it, all of you. Yeah.
So actually there is a recent paper from Apple. One student from UCSD, he did internship at Apple this summer and they published a good paper. And what they did is they combined general reasoning models, Gemini 2.4 in this work. And given and also specialized model that can spit out lean proofs. So what they do is, given a lean problem, they first ask the general reasoning model to come up with proof sketch or the general idea. It's not going to speak in lean, but give me some high-level idea or things to do, how to decompose the problem, any relevant lemmas, etc. And then they use the specialized lean model to kind of translate and solve sub-problems and then stitch them together to come up with the full proof. So I thought this is actually a very great example of how we can combine general but informal reasoning model and also specialized formal lean model, and how can we make synergy out of it. So that was really a great example. Good. And the paper name is Hilbert.
Hilbert, okay.
You want to answer?
Yeah, I think this is very great point. I do think that we will have at some point an analogy of the Nature paper and the
But again, we need to, it seems to me that knowledge sometimes, discovering knowledge is not also a linear process. And it could be that the issues we are obtaining and observing all together as scientists or as communities are inherent to the process of discovering knowledge and not necessarily artifacts of our methods. It's I always go back to the very basic statistical hypothesis testing. We can never accept a null hypothesis. We can only not reject it. So the concept of discovering truth is more of us going no, 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 until we get to somewhere that we can no longer say no to. And I think all this idea and these issues and this observation we are making is a result of how we discover knowledge, and maybe not a bug in our methods. But just I don't know.
Yeah, I'll give one kind of wrap up answer and try to synthesize some of this. I think a lot of those kind of reinforcement learning, but also just a lot of science in general, is kind of finding that balance between exploration and exploitation. And some of these different approaches lean more on one, like being itself is even more of an kind of exploitation. You specify the thing, it goes and does the thing. But you still need the exploration is still something where the dimensionality makes it really impossible to brute force, but kind of sort of the AlphaGo or other approaches of like even like as an expert, I kind of like part of being an expert is predicting which directions are more likely to lead to something interesting, and I think that still requires a level of human synthesis and experience and socialness to make that happen. That I mean, I'm not going to say the LLMs aren't going to be able to ever do that, or some other version of AI won't be able to propose interesting ideas, because I think there's certainly room for that, just because the literature is so large and they can explore that and like look at things in this latent space in different ways. But I think there still needs to be some like kind of our consensus about science is not necessarily, it's still like kind of our, as a consensus, it's a discussion on people about what ways of thinking about the universe are useful where, and we know all of our models have issues, but even ones that have been falsified in various ways still are useful in a certain bound. So in that, I think there's still room to like figure out what those bounds are, and that involves like poking up against different directions and seeing where we hit walls. And with that, let's go get some food.
No.
Oh, it's not yet. Oh, no.
There's one more question.
Oh, okay.
How do you think your different methods like linear and XAI can handle the reasoning when turbulent processes come into play in your system model? Reasoning on kind of chaotic processes might be challenging, right?
Yes, they are challenging. I think with turbulence, there's certainly there's like the kind of average and dissipative components. So you can like it's easy to reason about the average and the dissipative parts, but this is where ensembles come into play, and the fact that the chaotic systems here are very sensitive to initial conditions, but you do have deterministic pathways and attractors that the systems do seem to be picking up on some of that. So I think there is room to learn, but there is a paper from a couple of years ago that was talking about how chaos may be a limiting factor in doing long range like back propagation through systems over like many days, because if you don't have precise enough numbering, you're going to run into issues with how much you can update the model. What like just your gradients don't propagate well, and work by I'm blanking on his name right now. He's professor at University of Washington who's doing basically the idea is using back propagation to update initial conditions to increase the likelihood of the model predicting a heat wave or other things like that. That actually works pretty well. You can actually optimize out to like 3 or 4 weeks but only out for 3 or 4 weeks if you use float 64 precision. If if you're a float 32, you can only get to about 2 weeks. Greg Hakem, that's the professor for that. So some really interesting papers in that space, and we've been playing around with some of these techniques as well. But there's an implication that there's more predictability, but only if you know what the future is. So the real like if there's other precursors we can figure out either in the initial condition space or in bias correcting the models, there is a potential higher, like longer range predictability we might be able to reach, but it still remains to be proven if we can actually reach that.
That seems like a great answer. Is that good? All right, then. Robin, I hope that worked for you as well. And thank you so much to our three panelists.
We'll be back here at 1:30, so you're like 55 minutes. Go to the cafeteria and there's the reserved area at the end.
Yeah, I think I have a lot of.
Thank you so much. Very nice moderation.
Yeah, thank you for your questions.
Great questions. Exciting discussion.
I'll just say that this afternoon, we have 8 talks, so we have 4 20-minute slots, and then we have a half-hour break for more food and socializing, and then we have 4 more talks, and then happy hour. So, a few of the talks are going to be by remote speakers. The first talk is by Chinmayi Baramashetru. Sorry, I probably did that wrong. About a lightweight verification strategy for climate coupler correctness. So go ahead.
Sorry, am I audible?
Yeah.
Yeah, okay. So, hi, I'm Chinmayi, and today I'm going to present a joint work with Dominic Orchard at University of Kent and Cambridge. And the talk is about towards modeling and verification of coupler behaviors in climate models. So to start with, so a brief overview of climate models and couplers. So first, we know that climate models are large-scale models that simulate Earth's climate over time. They use physical laws and numerical methods and observational data, and large part of the code is still implemented in Fortran. And they're usually composed of many interacting submodels, each operating on different grids and resolutions and time steps. And here, if we think about the software architecture of these software models, there are 4 diagrams here, which shows the interaction between several submodels, and all of them are connected through a single piece of software, which is coupler. And the model interaction is usually coordinated by the coupler, and it performs various tasks such as field exchange, interpolation, conversion between different grid formats from one model to another, and time synchronization between various models, and which is also why it is critical for reproducibility, scalability, and correctness in general in multi-component simulations. And even a slight error can distort scientific results. So it's not just about software correctness anymore, it's also about the scientific results or scientific correctness, scientific software correctness. So one of the big problem about climate model verification is the scalability. So verifying a full models is extremely complex, as we know, and couplers represent a very tractable verification target. So they're critical, and they're shared amongst several other models. But these couplers themselves are developed over many, many years. They're complex, and they're loosely specified software orchestration layers, especially about the behavior of the code, and which also makes it hard to ensure correctness and reproducibility. And if we think from a software engineering perspective, conceptually, they are very similar to modular reasoning or model-based software engineering, where you have several components, several contracts coming in play, and also modular reasoning between various models. So before going into like how we approach coupler correctness from a formal verification perspective, I want to quickly go through the state of art of formal verification techniques that exist. So first is testing, very widely used approach. We saw some tutorials yesterday highlighting various testings, that is property-based testings or unit testings, and they give you quick feedback, but they inherently do not guarantee any sort of completeness. Then we have static analysis, which is where you analyze your code without actually running it. We're using some information such as your type information or control. You do some sort of control flow analysis or data flow analysis, and you reason about your code using that information. Next is we have deductive verification. So this approach uses like a logical reasoning to prove that your code always satisfies a formal specification. So yesterday we saw some tutorials which gave these specification in terms of a precondition, postcondition, and invariance. So these will be your specification, and you sort of discharge those conditions into a solver, such as the SMT solver or the Z3 solver, which we saw yesterday. And this solver tries to prove that those conditions hold for all possible executions, right? So that is your deductive verification approach. And talking about proof assistance is where it takes one step ahead, where these produce a machine-checked proofs. For example, for today's talk on lean, or we have Rock or Isabel, which are these interactive theorem provers, which helps to generate machine-checked proofs. And typically they operate on since it can be quite time consuming and quite difficult to do it, and it's very manual process, so they focus on a verified kernels or compilers, not in a large scientific applications. And then we have model checking, which is explicit, symbolic, and it's bounded, and we build a finite model of a system, and then you automatically explore every possible state to make sure that the certain safety properties always hold. So that's checked in your, that is model checking. And one problem is that you often face is the state becomes so big, then you have a state explosion problem in model checking usually. So verification, where does it stand in climate models today? So testing is by far the dominant approach. Most modeling centers still rely on regression tests and some physical sanity tests. And beyond testing, there are some approaches here, the ones that we see, which is using interactive theorem provers such as Rock or Isabel. And they try to verify numerical kernels, such as the Taylor models here, or the Lorenzo retractor algorithm. So they typically focus on, as I said, small self-contained algorithms, but not like a full production models. So largely the verification is still on testing. And another key aspect that I have to talk about is the dominance of Fortran in climate models. So if one were to migrate Fortran code completely into modern languages like Python or C++ or Julia, for instance, it's going to be extremely expensive, of course, and also like it's hard to guarantee any sort of bit-for-bit reproducibility in these languages. So Fortran, another problem is it lacks modern formal verification tools, or it doesn't have a mechanized or semantics or for Fortran, which makes it harder to come up with any of these tools. So there is a huge tooling gap which limits the deductive reasoning or automated correctness proof that could have been explored in Fortran. There are some attempts like at the level of research prototypes like Camphor, which have explored static analysis and specification checking and they do deductive reasoning in that front, but nothing to an extent that it could actually be applied in real systems. So in the next half, I'll just briefly present our approach for this. Before that, so some of the major coupler frameworks that is out there today are like CPL6 and CPL7. We have the ESMF, which is Earth System Modeling Framework, which provides like a general purpose infrastructure that supports these couplers. And then we have Modeling Coupling Toolkit, which is more like an embedded library that has been used by other couplers. And then we have Oasis couplers, also very widely used in many of the European models. So when we compared all of these major couplers, what we found out is like while their implementation differ quite a bit, they revolve around some underlying set of tasks or responsibility. For instance, like the couplers themselves, like some of them are standalone, some of them are embedded libraries. They handle data exchange or they handle timing or interpolation slightly differently, but conceptually they all perform a similar set of operations. And based on that, we sort of systematically looked into them and defined a set of 4 core functional modules that can serve as a basis for our formal reasoning and verification, which includes the configuration and initialization module, a field registration and metadata module, a grid manager and interpolation module, time synchronization module, and data transfer and routing module. So once we identified these common functional areas, we looked more closely into what each of them does. For instance, here configuration module, what it does is it parses an external configuration file. It defines the components which are active, how do they connect, and what data they exchange. The field registered all the metadata that it has, the units, the grids, and about the coupling fields. And then we have a grid manager, which basically have the grid definitions and how do you calculate the interpolation weights and how the remapping is done from the source field to the target field. And time synchronization, where it manages how the exchanges occur, in what intervals and schedules. And the last is data transfer, where the exact communication pattern and data exchange happens. So together, these modules form like an operational way of looking how different, how these tasks can be generalized into these separate modules that can be treated as like a general principles of couplers. So here is a small example for one of the functional modules, which is a time synchronization module, which can be represented using formal contracts. So by formal contracts, I mean that you represent your requirements in terms of the whole triples, which I call, which is preconditions, postcondition, and invariants. So the goal of this module is to ensure that the old couple system advance in lockstep and exchanging data are at a correct simulation intervals. And to make their behavior explicit, we define the precondition. We say that the components align and the clocks are consistent. And the post-condition is data exchanged once per every step, and there is no like duplicate transfers or no missed transfers. And the invariant here will be that the simulation time, there is a time monotonicity, that simulation time never goes backwards. So these behavioral properties usually can be expressed as contracts using a behavioral specification language like ACSL, which is used in C, or JML, which is used in Java, which can enable contract verification and module behavior. But another thing to note here is like we don't have such a behavioral specification language for Fortran. So that is another important thing to note. I'll show a small coupler interaction flow here and where exactly our approach plays a part. So here we have a simple workflow, a coupler interaction between two submodels from ocean to atmosphere, where the coupler receives the data, processes, and sends it to another data. And our approach is introducing a dynamic contract verification into this interaction flow. So we extend the setup by inserting a runtime contract checks at the coupler boundaries. So what these checks do is they monitor for data consistency, they monitor for timing as the model runs, and it verifies that the data are exchanged when expected, and all the components are synchronized according to the modules that we define. So the assertions that we use here aren't like arbitrary, they come directly from the formal module contracts that we defined earlier, that is covering synchronization, interpolation, or data transfer behavior. So this means that we can automatically check module level correctness during execution, catching issues like missing data exchanges or inconsistent timestamps, and all while being compatible with Fortran. So how we make this work is we use Pharmacy, which is a deductive verification tool for C, and its EACSL plugin, which is the runtime assertion checking plugin. And Fortran allows this ISO C binding through which you can expose the C interfaces where the runtime contracts are inserted. And each contract describes what a coupler is expected to do and when data should be sent and what timing constraints. So Pharmacy then, through its EACSL plugin, it automatically instruments that code and monitors those properties at runtime. So in short, it's like bridges a way to combine with the legacy Fortran couplers with modern verification approach by using a dynamic contract verification. And you can actually check like functional behavior of a coupler rather than treating it as a black box in a way. I don't know how much time. Okay. So to wrap up, the couplers, they make a tractable verification target in Earth system models. And despite different implementation, they share a common set of functional behaviors that we extracted. And from our analysis, we show that these behaviors can be captured into verifiable contracts for different tasks. And these contracts form a basis for like a clearer design principles and modular verification for couplers. And our approach supports two things. One is retrofitting the existing couplers with verifiable contracts, where these modules come in picture and then you insert them and then you make a runtime verification. And then if another aspect to it is like designing new couplers from scratch, and these can be treated as a design principles to have formal verification in mind when you come up with a new coupler design. So the next steps here are to build a minimal contract framework for existing couplers such as Oasis, and you bridge the legacy Fortran system and to assess reproducibility and performance when it's done. So this work is presented at Propel, which is a Programming for Planet workshop, which was co-located with ICFP this year. You can check the paper for more details. It has an example that we took, and we showed how our approach would help find that bug. And thank you, and I'm happy to take questions.
Thank you. Any questions for Chinmayi?
Yeah, so this is fascinating. I love this kind of work, verifying things that happen in the coupler layer. So I work on the CESM, so one of the coupled models. So we do have some of what you were talking about in place. It's not as it's not as clear as what you're talking about here with the preconditions and postconditions and invariants and things like that, which I think we could improve our code with that, which I think is part of your point is about the design. But I'm thinking about how to apply it in our model. And it seems like we have some assertion, we have an assertion construct that seems like we could use. And I think that's part of what you're saying is that, if we use assertions and things like that, we're going to make sure things are, in sync the way they should be, things like that. I think that's kind of the bottom line is you're talking about the design of couplers such that they have these contracts and they checking for invariants and these kind of things. Does that sound right?
Yeah, that's one thing that I noticed, because most of the couplers that are in place right now, they except ESMF, which has introduced some sort of these design principles in their framework, and most of them don't have a framework that you can or there's modularity that you can think of. And then another thing here is the contracts that we talk about here is like, you can have a code as a runtime assertions in your Fortran models to do that, but instead the approach is slightly different. So where if you have a plugin, if you have a tool like Pharmacy and you annotate your code, the Pharmacy automatically converts your contracts into a code, and then that is converted as a runtime assertion. So you don't really have to write or code or bother to write this ad hoc code. You just write the contracts in your specifications, and Pharmacy directly automatically converts that contracts into code, and then that is checked at runtime. So it brings much more a cleaner way to do this. I don't know if it's a cleaner way, but it's more it's like you define the contracts and you focus on specification, and you don't focus on how that specification is instrumented. So you write your specification, you think of, okay, this module needs these preconditions, I need these postconditions, and this property, for example, your energy conservation or something, and this property should hold for this model. And then you just give those contracts, and that gets converted into code, and then you just do runtime verification about it. Yeah.
Okay, I didn't catch that because you had like those comments that showed the specifications, but what you're saying is that turns into code by just adding in the comments, and that is beautiful.
Yeah.
I love that.
Yeah, exactly. Yeah. So that is done through the specification language, which exists in most like Java and C, but it doesn't exist for Fortran. So what we did is to just leverage in C, because there is a workflow that already exists in C, and through Fortran we are just we use Pharmacy to get this sort of advantage. Yeah.
Right. Cool. Okay. Thank you.
Thank you very much.
Yeah.
Right. Our next speaker is Carolyn Begeman, and she's from Los Alamos National Lab, and is going to talk about the next generation ocean model, Omega, that's part of E3SM, the DOE model. And Carolyn was going to be here in person, but then Los Alamos axed all travel, so I'm glad you could make it virtually.
Thanks. Yeah, I'm really happy that I still have the opportunity to present this work, and it's been a really fascinating slew of talks and panels so far. So thanks a lot for organizing and coming up with a lot of great insights. So today, as Allison said, I'm going to talk. Can you hear me? Oh. Are we having technical difficulty?
We can't see your slide.
It cannot. Okay.
It says all I can see is it's like a little strips, like it's not showing the whole window or something. It's just like a little piece.
Okay. I'm going to quickly try to stop and reshare.
Mm.
Give me 1 second. Sorry, everybody. It worked yesterday.
Try sharing just your PowerPoint window.
That's actually what I was doing before. So I am going to try sharing this this window and see if that works better. Okay, does this work?
Yeah.
Okay, awesome. Sorry for the delay. What I was going to say is that today I wanted to talk about the steps that we're taking toward verification and validation as we generate the next ocean component for E3SM, which is the Energy Exascale Earth System Model developed by the DOE. So, as some of you may know, E3SM is pursuing a phased replacement of its core model components. And this is motivated by the fact that we just couldn't get the GPU speed up that we needed from our legacy Fortran code. So this process has already been well underway for the atmosphere component of E3SM. It's been ported in about 5 years, and they were really shooting for bit-for-bit implementations, at least in version 1 of that model. What we're pursuing for the ocean component is largely a direct port. So you'll see a few slides in here that pertain to benchmarking the new component against the old, but we're not actually going to aim for bit-for-bit reproducibility. Our current ocean code is called MPass Ocean. As I mentioned earlier, it's written in Fortran, and we tried to get performance portability with OpenACC. What we're pursuing now is the new ocean model we're calling Omega, which is written in C++ using Cocos. And so far, we're seeing about a 40 times speed up from CPU to GPU with Omega, whereas with MPass Ocean, with a reasonable investment of time, we couldn't get more than 15%, which is pretty abysmal. So with that motivation, I'm going to present some of the strategies that we're using for Omega testing. We're aiming toward testing alongside continuous integration. So with each code change or a GitHub pull request, we're running unit tests and whole component tests. We're not yet hooked up to E3SM and coupled with all of the other components. So I won't speak to any of the coupled model verification activities. For the purposes of this talk, I'm also going to set aside the unit tests, which we're accomplishing with C-tests, and focus on the whole component tests. So what kind of whole component tests are we talking about here? Kind of at the foundation is our verification tests against exact solutions wherever we can accomplish this. We also have a suite of convergence tests. As I mentioned earlier, it's important to us to be able to benchmark Omega against MPass Ocean. So we have tests in which we do that. And then we also run comparisons for each of these GitHub pull requests against our baseline configuration. So comparing of a model with a new feature against the master branch to make sure that we haven't broken anything. In the future, there's kind of a handful of tests that have some validation against observations, but these are not as numerous as one would like, especially for a single component. These often look like verifying the fluid dynamics against laboratory experiments and those kinds of things. Okay, so how can we automate these whole component tests? So with unit tests, where those are automated with C tests at build time with an argument to CMake. But for these whole component tests, we are making use of a Python package that we're developing in-house called Polaris. So this Python package is combining several different features. The first of which is mesh generation, which we do with external packages. We have a command line interface that sets up and runs tests and test suites. It reports back a pass or fail based on the test output and or comparison with a baseline. I'll talk a little bit about how we get interoperability between models so that we can compare our prior ocean component with our new ocean component. And then we've also embedded some visualization capabilities because our native unstructured mesh has historically been difficult for folks to visualize and come up with visualization routines that are robust on their own. So we're currently running these test cases in serial, where each test is run on multiple nodes, and we're working toward running these test cases in parallel. Okay, so how can we make testing approachable to developers? One of the main ways we do this is by having an intuitive command line interface. And this is after setting up a Conda environment that supports the builds for our ocean components. And setting up this Conda environment is usually the biggest step for a developer to start to engage with this Python package. Here are just some examples of the command line interface. We have options for setting up single test cases, suites of test cases, comparing branches of the same model, and then, as I mentioned earlier, comparing here between different ocean models, MPass Ocean and Omega, which are both run on the same unstructured mesh. Okay, so once a developer has run a test suite, we output the results to a log file. And the idea is that this provides kind of a quick view of what features are functioning, and also provides some output that developers can paste to a GitHub pull request. Each test itself is designed to be relatively computationally light. Our tests right now take less than 2 minutes on less than kind of a handful of nodes on some of the supercomputers we generally use for E3SM. The whole PR suite itself can take up to an hour on a handful of nodes. So we're aiming for something that's relatively light, and as I'll talk about a little bit later, we're moving towards automated nightly test suites as well. Okay, so one of the main features that we have added to this testing framework that we didn't have previously is the ability for multiple test cases to depend on the same step. Steps here are kind of a formal Python class that describes the like literally the steps that are involved in a particular test. So here's an example of an advection test on the sphere. Previously, we would go through and set up the mesh, run some initialization step that populates the initial conditions, and then run the forward model and do some analysis. But many of our spherical tests used similar resolutions. Say we have a convergence test that runs a range of resolutions. You wouldn't want to develop the same mesh twice for different tests. So with this new framework, we're using dependencies between steps to only run one instance of each. And this also forms the basis for the task parallelism that we're shooting toward, where we're really using dependencies between steps and their inputs and outputs to exploit that parallelism. Okay, so how do we integrate these component tests into the workflow of Omega developers? So let's say a developer wants to add a new feature to the model. How would they use this Polaris package? Well, first, after designing and adding these new tests, they can actually make use of Polaris directly for looking at the physical behavior of the feature that they're testing. So for any substantive new features, we want developers to be designing and adding tests that are really going to show that feature does what it's intended to do. So in addition to the test of that feature itself, the physical correctness of it, we also test for bit restarts, domain decomposition, threading, chunking, and these are generalizable concepts in this Python package. So we also would want the developer to use this test and its corresponding viz for debugging wherever they can, and I'll circle back to this with some of the visualization tools later. And then when opening a PR alongside the unit tests, they can run this PR test suite with their branch. So it's supported on a variety of machines, compilers, CPU and GPU architectures, involves benchmarking against the master branch and our established model. And then, as I mentioned earlier, they can paste the results of this test suite into their PR. Okay, so since one of the main motivations of this package is benchmarking between MPES Ocean and Omega, is really important to us to create a framework that would allow folks to do this comparison in like environments and with as identical of setups as we can get. So as I mentioned before, we're using the same meshes for both components through this framework. And we have the same Conda environment that's supporting builds of both MPES Ocean and Omega. And then the configuration of the model and the output is just set up identically with the YAML file that basically has a dictionary of the mapping between variables and configuration options. Okay, so I'd like to present just a few of the example test cases that we include when we're testing Omega and benchmarking. So we have a suite of kind of classic tests from the literature. One of those is sort of the Monk barotropic wind-driven gyre case that any ocean modelers will be familiar with. Here we're using it to test lateral boundary conditions in our model. So both free slip and no slip boundary conditions have analytic solutions available. So here we're seeing that at least at this resolution, we're not getting quite as much of a free slip boundary condition as we would expect from the analytic solution. We can also use the method of manufactured solutions, which is a great way to verify complex nonlinear equations like Navier-Stokes. So the strategy is basically choosing some analytically tractable solution, inserting it in the left-hand side of the equations. Here, I'm showing the nonlinear shallow water equations with biharmonic viscosity. And then we add source terms to the right-hand side to balance it out. And this particular test case is based on the work of Sid Bishnu, who worked with our group for a bit. So here we're using the visualization that's native to Polaris, plotting up a comparison between the numerical and analytic solution for a range of resolutions. And reporting the convergence. So for this test, we have a threshold for the convergence. And if it doesn't pass the second order convergence, the test case will fail. We also have a number of diagnostics that can help developers understand things like numerical mixing. So in this case, we're evaluating numerical mixing in horizontal advection test cases and vertical advection test cases separately. So some of these spherical cases are based on this paper from Lauritsen, and you can see kind of a mapping of the space where we're simulating real physical mixing as opposed to range preserving, unmixing, or overshoots. And their filament preservation diagnostics. And the figure on the right shows the resting potential energy evolution for an internal wave test case at a range of viscosities. Okay, so what we try to do with Polaris whenever possible is develop framework that makes it easy for developers to add new test cases. So as an example, we developed some classes that help us set up future convergence test cases and make it easier for developers to customize those tests at runtime. So in this case, developers can set the resolutions they want to test in a config file. We then have a convergence forward class that sets up a forward model run and sets the time step accordingly for each of those resolutions. And then finally, we make use of model-specific config options to determine resource allocations. And then likewise for generating convergence plots like this, here we have a convergence analysis class where the variable name that developers want to evaluate convergence on is provided. And then there is an overridable function that defines the exact solution for that particular test case. Okay, so switching gears a little bit here to some of the visualization methods that we're supporting. I just want to drive home how important I think this is for understanding model behavior because we work with both MPass and Omega on unstructured meshes. Visualization can be non-trivial for cell quantities, edge quantities, and vertices all have different kind of dual meshes that need to be generated and plotted. So one of our colleagues, Andrew Nolan, developed a Python library called Mosaic that sits underneath Polaris and helps with these visualizations. So here, are some plots of both cell-centered and edge quantities for planar horizontal fields. But we can also extend that visualization capability to global fields. Previously, when we analyze global fields, there would be some interpolation rather than plotting on the native mesh. And this can make it really difficult to see things like overshoots and undershoots. So here's just an example of that for a tracer advection case that's quite rigorous. So with a second order advection scheme, there are these overshoots and undershoots shown in the orange and black colors, but you can see that those are resolved with a third order flux corrected advection scheme. And of course you can also have errors that cause fails when these overshoots and undershoots happen of this particular test case. Okay, and then this is a demonstration. This framework can really be used to examine high resolution global test cases. In this particular instance, I'm showing the layer thickness of the top layer of a high resolution E3SM ocean mesh. So we can use these approaches to look more closely at mesh verification, but also look more closely at E3SM output. Okay, so finally on the visualization side of things, I just wanted to highlight that we're also enabling looking at transects through the ocean domain. And this was a real gap previously as developers previously used ParaView for visualizations and that didn't have this capability. So this is a lightweight way to really see what, say, transects through ModRise shown here on the right look like with meshes of different resolutions and probe tendencies. So here we're showing the evolution of temperature with horizontal mixing around this, giant seamount. Okay, so I'd like to just wrap up here with a few notes for our plans for Omega verification and validation with this framework. And I'd be really interested to hear your feedback about where you think we should take this work and how we can generalize some of this work to multiple communities. So right now, we have kind of a manual process for developers submitting these PR test suites. We're working now on adding nightly testing using Polaris with a nightly test suite and reporting those results to CDASH alongside the results of CTEST. We're also always working on improved code coverage as we develop this Polaris package alongside the development of Omega. We want to keep pace with testing each new feature as it's brought in, which is something that we historically have not quite hit the mark on with development of MPass Ocean. So we also want to report declines in performance as new features are added in, computational performance, that is. And then we also want to reduce barriers to entry for developers whenever possible. So for example, we have a build utility for Omega, and we'd like to have build utilities for both models. And this is great, not just for developers, but also for bringing students and collaborators onto our project. Okay, so as we move towards E3SM coupled simulations, there's a lot more that's important to look at. So mesh quality checks have not been done with the code that was publicly available and inspected. So we'd like to increase the formalism of those mesh quality checks. We also want to build out initial condition creation for those global simulations. And then use this same Polaris package for visualizing output from those coupled simulations. And we can extend this to our sea ice model and past sea ice as well, because it uses the same unstructured mesh. So I have the link there at the bottom to the Polaris repository if anybody would like to check it out. But I think I'll stop there and take any questions or discussion. I think we still have a couple minutes.
Anyone have questions for Carolyn while we get Michelle set up? Jesse?
Hi, Carolyn. Yeah, good talk. I was curious, at the beginning, you kind of mentioned you have baselines for various different tests, and then you try to run them on different compilers and architectures, I believe. I'm just kind of curious what your guys' like baseline strategy is. Like, are you trying to cover every possible combination of like compiler and test case and architecture, or is there like a subset that you're running to just save computing time and things like that?
So good question. For nightly tests, we're just running a subset. But periodically we do run the full suite on every compiler and machine combination for machines and compilers that are used regularly by E3SM developers. So it can get a little wieldy, especially the maintenance of Conda environments across all of these different machines. And now to support builds of 2 different components. So, but yeah, we are trying to, keep as much flexibility as possible, because we have allocations at a lot of different places for a lot of different projects.
Cool, thanks.
All right, thank you so much. All right, our next speaker is Michelle Harrold from NCAR, and she's going to be talking about METplus.
All right, thank you for the introduction. Yes, and the title, we're going to talk about METplus, which we kind of, the tagline is being a one-stop shop for trusted, reproducible, and scalable verification capabilities. And just to define kind of when I say verification, I know we've talked about verification a lot today, and everyone kind of has their own definition for their own application. So we're definitely going to be in the numerical weather prediction or kind of modeling space today. So how we look at model output and diagnostic output and compare it to observations. And I want to give a big shout out to all the folks listed on the slide here. The METplus team is comprised of software engineers, statisticians, and scientists. So I want to thank them for all the material. Not only they helped contribute to the slides today, but also to help keeping METplus a robust software package. All right, just a little bit of background about METplus for those who may or may not be familiar. METplus is a highly configurable verification framework, and it can span a number of temporal and spatial scales. So really high resolution model output at those really worn on forecast type scales, and extending all the way up to the climate scales at more coarse resolutions. It is a very community-driven verification package. It is open source, and we have a number of active partnerships, both at national and international operational centers. We work very closely with NOAA. Their verification system is powered by METplus. We also work with folks at the Naval Research Lab, and the US Air Force also uses METplus as their operational verification system. In addition, we work closely with people at the UK Met Office, the Bureau of Meteorology in Australia. So it really is a worldwide package that's not only used by operational centers, but we have a lot of usage at universities and the research community as well. And we're also starting to expand our reach more into the private sector. So given that METplus is used heavily throughout the world, it is also built to be extensible and scalable. We currently have over 150 different statistics and diagnostics that are supported. And we can support a number of point and gridded data sets. Given that we have a large reach, we also have very robust user support, and we do this through GitHub discussions. So we have a forum where folks can ask questions, and we usually try to address those within a day or so. And then I'll talk about this a little bit more later, but we also have what's called use cases, and we have these for easy spin up for new users to be able to start engaging with METplus quicker. So when it comes down to it, we hope that METplus is able to provide a versatile toolkit that can enable objective and reproducible evaluations over a broad range of weather and climate applications. So just a little bit of background on kind of the different components that make up the METplus ecosystem. So we have what's called METplus wrappers. And so those are going to be the black arrows in that figure on the left there. And these are kind of a Python suite that has a low-level workflow that kind of acts as the glue that keeps all of the other components of METplus together. Then we have MET, the model evaluation tools, which is represented by the orange rectangle in the upper left. And that's really the workhorse. That's what's computing the statistics and different diagnostic tools. MET's been around since about 2006, so it's about ready to celebrate its 20th birthday. It first came on scene when the US Air Force wanted to verify its high-resolution 20-kilometer forecasts, and has since grown significantly since. And in addition to our verification or the statistics, we also have an analysis tool package, and that's available for more advanced analysis. So we can do things like slice and dice the data, aggregate, and then do some plotting as well. So we do have a number of comprehensive point-based and grid-based verification, both in the traditional sense and also using spatial verification methods. And so I'll be highlighting just some examples in the coming slides of the different types of verification that MET produces and what METplus can do for you. In addition, it also supports deterministic, ensemble, and probabilistic verification as well. And not only does it do the verification component, we also have a number of capabilities for things like regridding, interpolating, masking, and reformatting your data so you can get it in the right form to verify. All right, so I'm going to spend a little bit of time talking about some of the examples of statistics and diagnostics. Kind of start off with just some kind of basic traditional types of verification here. And these are for deterministic or just a single model solution. So just some examples of time series plots. We can also verify upper air, vertical level type plots. So in addition to some more simple type of time series, we also have the ability to create performance diagrams, visualize data spatially, and then also create scorecards. So developers and decision makers alike like the scorecard because you can compile a whole bunch of statistical information for different variables and levels into one. So these are all different types of analyses and plots you can create with the METplus system. In addition to more deterministic types of verification, METplus is also great looking at ensemble and probabilistic verification as well. So we just have some examples of that going from reliability diagrams all the way to rank histograms and more. In addition, there's also tools in METplus to calculate probabilities. So this is just an example here in the lower middle, looking at how MET can calculate neighborhood ensemble probabilities. And there's a number of different methods that MET can support as well. In addition to more spatial types of traditional verification, MET can also handle spatial verification. So obviously, grid-to-grid verification is good as kind of a first step, but we know there's things like the double penalty effect and whatnot. And so being able to expand your verification capabilities, things such as neighborhood methods, such as fraction skill score, and other object-based methods is really helpful at getting its more diagnostic information related to your forecast. So we have a tool in MET called MODE, the Method for Object-Based Diagnostic Evaluation. And so just an example of how that works is if you look in the upper right figure, we have some model forecasts of composite reflectivity. And then just below that, we have the objects that MODE can create. And with those objects that MODE creates, you can calculate statistics. So you can get at things like, is my forecast displaced from the observations? Is it too intense? Is it producing too many objects, too few objects? Are they creating objects that are too large? And so you can get some really nice diagnostic information when you're looking at it in a more object-based way. In addition to forecast verification, we've also found that MODE can be helpful for more validation type activities. We did have a sponsor that was translating some of their model code from one compute platform to another, and they wanted to come up with some novel ways to understand if the implementation was done successfully. And so what we have here in this lower left figure is basically the difference between two forecasts that were run with the same code but on different compute platforms. And normally we'd expect not a lot of differences, maybe just some noise in the field. But we were actually able to identify some coherent areas and actual objects that were created. And we were able to deliver that information back to the folks that did the implementation. And they were able to trace that back to an error with the implementation. So we were able to use some object-based verification in the model implementation process. So that's just another kind of off-brand use that you can also use with object-based verification. In addition, we also support a number of tropical cyclone verification related activities. So we can do standard track and intensity errors, case-by-case basis, or over a full season. And lately, there's also been a lot of work that's been dedicated to more diagnostic information related to things like the radius of maximum wind. So you can see some nice examples here on the left of looking at azimuthally average, specific humidity, and vertical velocity. So these can get at things like characteristics related to the PBL height or the eye wall characteristics. So that's been especially helpful for some model developers. And then there's also some things we can do related to precipitation and making it storm relative. And then you can normalize by the maximum of radius wind, compare your observations and forecast. And we've also applied things like MODE to hurricane forecasts as well. So a large suite related to tropical cyclone verification in METplus. And then just to kind of throw up a smattering of other types of application verification that METplus can do, a lot of work has been done with cloud verification. So comparing like forecast brightness temperatures to satellite data, both with spatial things such as FSS or object-based verification, looking at PDFs or 2D histograms, things of that nature. Obviously, a lot of work done with fire verification lately. There's been a lot of focus on that. So we can use MODE, but in now the time domain to track fire spread over time and compare it to observations. And then also some dust smoke verification, solar verification, and then seasonal to subseasonal verification. So these are all areas that METplus has been exercised and has a number of capabilities. Finally, the last set of examples I'll show is just with AIWP. Obviously, there's been a big push towards evaluating AI. So on the left, we have some examples of some new sharpness metrics that are now available in MET that are kind of based on the Ebert-Uphoff study in 2025. Just looking at, again, some gradient line type statistics. Then another nice use of object-based verification was applied to some credit data recently. So on the right, we have some object-based verification of 1 hour accumulated precipitation for 2 different thresholds. And then on the upper set of panels, we have the MODE, the number of objects that were defined. Then in the middle, we have the mean object area. And then in the lower set of panels, we have the total object area. In this case, the black lines here are what's called the target. And I believe CONUS 404 was used. It's a hydroclimate reanalysis. And then the colored lines are different steps of the AI model. And so if you were just to take a quick look at this, I would see that obviously when you're looking at object counts, we see that the black line is higher than the colored lines. And then looking at something like the mean area, we see that the black line is lower than the colored lines. And so you could infer that, at least in this case, the target area is producing more objects that are smaller. And so this can kind of help get a better diagnostic feel for what's going on in your target and your AI model. All right, so I also wanted to hit on a little bit of how METplus can aid in reproducible science. And so when you run METplus, you have these configuration files. This is a screenshot. If you squint, you might actually be able to read it. But basically in the configuration file, you can define things like the different steps you want to run. So what tools do you want to reformat your data? Do you need to rebucket it or anything like that? And then the different verification types you want to do. You can also specify the times you want to run over. You can do this by initialization or valid time. Then provide the paths to the different files that you want included. So we have things like file name templates, and you can find the different data sets that you need. And then any sort of configuration settings related to the verification itself. So do you want to mask over certain areas? What type of interpolation do you want to do in different types of statistics? So we have these METplus configuration files that kind of act as a recipe file. So you can set it up and it'll do the exact verification that you specify in the file. So once we've kind of assembled this recipe file, we can put it in our archive of use cases. So we currently have over 100 different use cases that are supported, and they range a large number of applications and categories you can see here. But basically, if a weather model can produce it, we try to verify it. And so we have all of these different sort of example or use cases available on our documentation page. We use Read the Docs heavily. But you can get an idea. So say you're a new user and you wanted to verify your precipitation forecast. We have these thumbnails you can kind of cruise through, and you can click on that. And then it gives a really nice recipe on how you can run that. So it says what the input data is, the expected outputs, a sample run command, and basically the science that you're trying to do with this use case. And so we have these use cases all publicly available so you can use for your testing and getting easily spun up. So with these use cases, we found that they have a number of benefits, both from a scientific perspective as well as a software engineering perspective. So we found that they've been incredibly helpful with the testing of the actual code. Halley Gotway is actually going to be giving a talk in about another hour and a half on some of the more specifics and how we use GitHub Actions and Docker in our testing framework. So I'm not going to go too much into this, but we have found them to be incredibly helpful for keeping our code in good shape. But as far as sort of the reproducibility side of things, we found that METplus use cases are great because if you can share configuration files and have them be easily tractable, it can allow for consistent setups across users and systems. Sometimes when scientists start sharing code, it can turn into a bad game of like human telephone where you start with one configuration, they might want to do something, so you pass it on and it changes a little bit. And then 5 iterations later, you have someone that's computing like a super easy statistic like 2-meter temperature bias in a completely different way than you originally started. So we found that these METplus use cases can dramatically reduce configuration drift over time, as also any sort of introduction of human error. And so by having these nice, transparent, and traceable workflows, we've been able to keep the verification part of it and keep the fidelity of that on par with what we would want from a statistical software package. All right, so briefly, I'm just going to end with, if you're interested in METplus more, we do have a lot of help available online. So we have, as I mentioned before, all of our user guides are easy to navigate and use Read the Docs. We have over 100 METplus use cases if you're interested in getting spun up. So I have a couple of links there. And as I mentioned before, we also have a very active GitHub discussion page where if you're ever interested in wanting to use MET or have a question, you can come here. All of it's publicly available. So if we've answered a question in the past, it's still available. So that way you can get help from others' previous questions. Or if you have a new question, you can post it. And we typically try and respond within a day or so. And we can answer questions related to configuration, installation, plot generation, things of that nature. So if you have any questions, I would heavily encourage you to check out our GitHub discussions page where there's a lot of information there. And I'll just end with putting up a couple of links here and give a plug that we have a minor release, 6.2, coming out hopefully within a week or so. So if you're interested, feel free to grab it. We have a QR code here that links to a number of resources, including our GitHub repositories, the GitHub discussions, tutorials, things of that nature. So thank you.
Any questions for Michelle?
Yeah, this is great. I'm curious, what kind of platforms you need to run this on? Is this something you can do on kind of a personal computer, or do you need something like Derecho or Casper?
No, actually, so you can run it, I run it on my Mac. We have a content installation, so you can grab that and it's hopefully quote unquote easy to install. But we have a number of pre-built executables available on things like Casper. So if you're ever interested, we do have a built-in Casper, a number of other HPC in the community. But it is not particularly resource intensive, so you can run it on something like a personal computer.
Okay, great, thanks.
Anybody else? All right, that was really great. And we have one more talk before the break, and that is Salil Mahajan, and he is from Oak Ridge National Laboratory, talking about assessing statistical reproducibility of AI and ML. So Salil, go ahead.
Hey, can you see my screen?
Yeah.
Make it full screen. Me. Okay, still see it?
For presenter notes too, though.
You want to switch display in your presenter notes?
There you go.
Is that, oh, should I, if I go to full screen, you're seeing the presenter mode? Are we good?
Not in the presenter mode.
Oh, okay.
Now just click where it says switch display. On the top left. That third icon, the top, there you go.
Third.
Yes.
Yeah?
Perfect. Yeah, great.
Okay, sorry. So thank you for this opportunity. This is a great conference. I was there 2 years ago. And so this work is motivated by the recent developments in AI/ML surrogate models of weather and climate models, and the possibility that we can now run very large ensembles with these models. So our motivation was, okay, if we can run so many large ensemble members with the model, is that ensemble going to state spaces where a dynamical model would go? And that's why this thought of checking the statistical reproducibility of this came in. But in order to do that, one thing that we would likely need is a large ensemble with a dynamical model so that we can compare with a large ensemble with an AI/ML model, ideally. And so our approach has been to use an ultra low resolution model, dynamical model, and then it's computationally much cheaper. And then you can run a large ensemble with that. And we can use an emulator. In this case, we use ForecastNet, and then emulate that low resolution model and then create a large ensemble with it. And now we have two large ensembles that we can compare for statistics. And within the E3SM project, we have this testing framework that can compare large ensembles. This is mostly designed for cases where you cannot ensure a bit-for-bit reproducibility, but you need to think your model is going to give you the same climate, and it's a test built for that. So this was the motivation for this. And this is a collaborative work between Michael, Ming, and I. All of us are at Oak Ridge right now. So let me get into it. So again, the motivation is that there are all these AI models that have come up, and we have had these recent talks about ensembles too during this session and the session before. And we can see that there's a lot of scalability that's offered by these models, and the order of 10K, maybe more, 40K in ForecastNet, for example, in the paper that they cite. This is because of both the use of GPUs as compared to more CPU-heavy dynamical codes. And then, so they are becoming a potential alternative to these traditional physics-based model, as we see with the ECMWF's AIFS model that's being routinely produced for weather forecasting and further. And then the other question is of fidelity, and there are lots of studies doing validating these models. And our approach here is to look at the ensembles of these models and see if which are very cheap to produce, and see if they're in the same state space as a dynamical model. And so that needs to be validated. So there has been some work, but it has not been looked at heavily. So our goal essentially is to do a hypothesis test where you want to show or test if the ensemble generated by a dynamical model is in the same statistical space as an AI/ML large ensemble. Okay. So, so just for review, this is the error growth in dynamical models slide. There are a few papers that look, and there have been lots before this, that look at the growth in errors in dynamical models. If you do a machine level perturbation in a climate model or dynamical model, you'll see an error growth that grows very fast. So for example, in this first plot here, it grows like order 8 in about 2 days, the error growth. And then on the plot in the bottom here is if you do an ensemble with initial condition perturbations of that order 10 to the power minus 14, you see that these errors grow and then they saturate at about 20, 21 days, 3 weeks timeline. And then you have this spread in the ensemble, and you can say that they're essentially decorrelated with each other. And on the top here is a plot similar for the ocean, the other two plots for the atmosphere. And in this case, the red line is just the default impasse ocean low resolution model. And you can see instead of like days in the atmosphere, it takes a few months for it to saturate, but then it reaches there, and all you see is a seasonal cycle up there. And so there is this growth in the errors that happens in the models. So again, our hypothesis was, do we see this in the AI/ML models? And so there has been a study recently that looks at this, and with this very interesting paper titled "Do AI Models Exhibit the Butterfly," or something like this, exhibit the butterfly effect. And what they have done is they take the Pangu weather model, and they perturb it, or they run it with initial conditions that are brought from the ensemble data simulation from ECMWF. So the order of perturbation in those cases is about 0.1 Kelvin to about 1 Kelvin essentially. And when they do that, this is if you look at this plot, can you see my mouse? Sorry. Yes? Yeah. Okay, cool. So in this, you can see on the top, these top two lines, the red line here is Pangu weather. The blue line here is the icon model. And you can see that there's error growth when you have these order of changes about this. And what this is showing essentially is the variance in the ensemble spread essentially. So this is a measure of how much the ensemble spreads with time. And you can see that with the blue line, it's going up and the ensemble is spreading and they're getting more decorrelated with time. And this is about a factor of 2 less than what you see from the dynamical model. And that's the AI/ML model. Now, this is for very large perturbations, and we had some discussion about this earlier in the day. But if you bring this perturbation down to about 0.01% or such, so about 10 to the power minus 5 order, and now you see that this is the red line here is the machine learning models, the Pangu, and you see that there's essentially no error growth with time in the model, but in icon or low res or high res. So the low res here is the blue line, and the high res is the red line. And so these are all, so the low res model is 50 member ensembles, and you can see this increase in ensemble spread by 72 hours, and nothing in the AI model. Even with high res, where they only had 5 members, they can still see this increase in ensemble spread. So essentially showing that the AI models are constrained in their sensitivity to initial conditions. So with smaller perturbation initial conditions, you don't get the growth that you see in dynamical models. So with this in the back of our mind, so we did this. Our approach is, as I said earlier, is to use a very lower resolution models. In this case, we used a 500-kilometer model version of E3SM, and run a large ensemble, train forecast net on it, and then run a large ensemble with ForecastNet, and then evaluate these two models. So just to talk quickly about the dynamical model that we have, the E3SM-v3, it's DOE's model, and it's about 500 kilometer resolution, and it's used for nightly testings. There have also been some studies looking at this, the quality of simulation of this model, and it includes for the full physics, so it runs the full model just at a lower resolution, and it's very cheap, and you can run 1,000-member ensembles with this. So that's what we did. We ran a 1,000-member ensemble for just the month of January, and we perturbed it by 10 to the power minus 4 Kelvin, given that we know that it's not very sensitive to initial conditions. And then we save daily data, and then we use that daily data to train the model, and then also to evaluate and so even though it's a very low resolution model, so the final scales are not there, but still you can see a growth in the error. So this is just a plot of the root mean squared error using a control run as a comparison. And we can see that if you take one run as a control run and take the RMSE value or a relative difference, you'll see that it grows with time, and you have this big spread by the time of this. Even though, so it's not as exponential as you see with standard resolution models, but still it's an order growth in about 10 days. And the emulator we use again is ForecastNet. It's NVIDIA's vision transformer model for weather prediction. They use an adaptive Fourier neural operator. They have moved on and have started using the spherical Fourier neural operator. But this is the older version that we use here. And this, we include like 20 variables, the state variables, humidity, MSLP, and other things. And so we train this emulator on 250 members of the 1,000-member ensemble that we had from E3SM-v3, and then we keep 750 of them for validation. And again, these are all run for January. Okay, so just to a quick plot of what the skill of ForecastNet is. So this is from the paper that discusses ForecastNet, and this was a very high resolution, about quarter degree, trying to mimic error 5. And what they wanted to show here was that the atmospheric river events are predicted very nicely at a lead time of 36 and at 72 hours. And they stressed that it's 45,000 times cheaper than IFS itself. Took 22 seconds to run a 100-member ensemble as opposed to 275 node hours for IFS. And on this side here is the skill. So it's slightly off than IFS, but it's still, given the 10,000, 45,000 times cheaper, it's not it's amazing. So now the model that we trained, so this is ForecastNet. So this is the plot of omega 500, and you can see that there's some skill in the model. And on the left-hand side, you have this ForecastNet. On the right-hand side, it's V3, the ultra high res. And if you take of the 750 runs, you assume one is the control, and the rest are your predictions of that one run, and just bring the difference being that there's a perturbation in the initial condition, and you compute the RMSE, and this is what you get. So in this case, with the perturbation of 10 to the power minus 4 Kelvin order, there is no spread in the ensemble at all. It's exactly the same. So this is similar to the Cell's paper, where they didn't find anything, and when the difference was like 10 to the power minus 5 or such. But you can see this. So it's nothing as compared to the model. Then, so what we did was we took the 10th day in January. So by that time, the errors, which were initialized with 10 to the power minus 5 minus 4 perturbations, are now at the order of 0.1 Kelvin in the temperature field. And now the forcing is big enough in the initial perturbation that ForecastNet responds. And so this is that plot. So when you have a bigger perturbation in the initial conditions, and you let the model run, and you see a spread that comes out of the ForecastNet ensembles. But this is, again, much smaller than what you see from E3SM-v3 low-res model. And it's even, so the skill is a little poorer in ForecastNet, and maybe you can tune the ForecastNet better. So we played with a few things. This was the best that we could get, but in none of those cases did we see that the ensemble spread is increasing. So this is one plot from that. And so there are 20 variables. We looked at all 20 variables. This is another. This is E500. Again, there's growth. There's a spread. There's a growth in the error. There is some spread in the ensemble, But again, it's constrained and it's much lower than what you can see with the dynamical model. So again, it's confirming what we found with the cells paper, but this is using a large ensemble with a much smoother dynamical model, and even then the forecast net seems to be deficient in this case. So with this, you could also look at extremes, and since we know that the ensemble spread is low, the extremes would also be weaker or not going to places that we see in the dynamical models, and that's what we see here for the zonal wind speed on the right, on the left, on the side, and for near surface temperature. So even the spread of the extremes is lower. So in these cases, visually you can tell that yes, the model is statistically different than the dynamical model. And so we didn't do any formal tests here, but we have a framework that does that. Within E3SM, we have a framework called EVE, which compares different ensembles just to test if they're in situations where there's a non-bit for bit case, and it tests for multiple variables, so on the order of tens to 100, more than 100, and then we have an immense database of false positive rates of these tests and false negative rates, and this is just an example on the right of the test for false negative rates, where in these days the model has been bit for bit, but still, if you run these tests with ensembles, you see that there are days when the test fails, and that's an example. So we are looking at these and trying to improve the false negative rates and the false positive rates of the model. So that's what I had for this, and so here's a summary of that. So we evaluated a very large ensemble of an ultra-low resolution dynamical model to compare against a very large AI model. So this is in the order of 750 runs. And we find that for large perturbations, which is equal to about what you get from ensemble data assimilation, order 0.1 to 1 Kelvin, and the forecast spread is there in the AI models, but is significantly constrained. And as a result, the extremes also are weaker. And if you go for even smaller perturbations, 10 to the power minus 4, and by projection lower states, there's virtually no variability that comes in this ensemble spread. And so this means that this could be because of the structure of the emulator. So we tried multiple things using different number of blocks for the Fourier neural operator, different width for the tokenizations, and a couple of other things, and nothing seemed to have increased the variability, even though the skill was not at par with the 3SM in most cases, slightly weaker. And so in the future, there are new updates to ForecastNet. So for example, this is the spherical Fourier operators that they use. And they also have better approaches for creating ensembles where they seed the model, or they have seed the model itself, meaning that instead of perturbing the initial condition to generate an ensemble, you perturb the model itself using something like a variational autoencoder, which will add noise to the model itself, and that would be a better generator of ensemble noise or ensemble variability. And so once we get closer, we can apply our tests from the EVE framework or that's in SEAM as well, and use those. That's all I had, and I'm open to questions.
Thank you. Questions?
Thanks, Salil. It was great to see the comparison with the E3SM and the ForecastNet. So do we have any hypothesis into why the spread is not that much in ForecastNet?
There are a couple of things that people have discussed. I have not thought much about this, but it seems because the precision of the model is one thing that comes into discussion sometimes. And maybe because we can go higher resolution, but with so the paper with cells, they were looked at Pangu, and even with very high resolution, they were finding this. So I'm not sure if the same applies to ForecastNet.
Thank you.
Fail.
Yeah, thank you very much. I think it's really interesting. I really like that CELTS paper, so it's great to see sort of replicated work on other models. Which, yeah, it just feels like very important because I feel like this cost cheapness of the ensembles is often so put forward as like the main benefit. And it's like, if those ensembles aren't so meaningful. Yeah, I was curious, you mentioned at the very end, these other approaches of seeding, or I've heard other people maybe talk about sort of like, you need to perturb continuously through the model, like not just the beginning. Yeah, do you have thoughts about whether that sort of violates the goal of achieving ensemble spread at all, if you're sort of like continuously pushing the model to spread artificially?
Yeah.
I don't know, it almost feels like, are you sort of circularly creating the spread or something? I don't know.
Yeah, and then it becomes hard to compare with what kind of models are you going to compare it with? Is it a fair comparison between an initial condition perturbed ensemble to an ensemble that is pushed at every few steps or every step? So there are questions about that. I'm sorry, I don't have a good answer for that yet.
All right, well, thank you very much, Salil.
Yes.
We're gonna take a 25-minute break. We'll come back at 3:20, go out, get some caffeine and get ready for 4 more talks. Yeah, thank you.
Different regular days. So we have Balvinder Singh talking about MAM4X. This is a fascinating topic for all of you climate folks. Even I kind of know what this means. Yeah. So thank you. Okay, take it away. Yeah.
Hi. Can you guys hear me? Okay. Okay. My name is Balvinder Singh, and I'm going to present MAM4XX talk. It's a performance portable aerosol model for E3SM. E3SM, there was a talk before, 2 talks before about E3SM, so it's a DOE Earth system model. And we see a large team here, and it's a collective team effort, and I'm really grateful to all the co-authors and collaborators who helped develop this model. So what is MAM4XX? It's a, like I said, it's a prognostic aerosol model, and it sits within EMXX, which is an atmospheric model in E3SM, which is completely rewritten in C++. And MAM4XX is also completely rewritten in C++ using COCO's performance portability library. And it's a detailed prognostic aerosol model. It models all the aerosol processes. Aerosols are tiny particles in the atmosphere, and they undergo a lot of processes like wet scavenging, dry scavenging, where they are scavenged, and there are production terms where nucleation and a bunch of other operation, and then they also interact with cloud. So there are aerosol cloud interactions. So it's a pretty detailed model. It sits sort of in the middle. We have more detailed models than this, but MAM4 or MAM model is pretty good for a global climate model. And it also, CESM also uses MAM4 physics. And MAM4XX is, of course, based on MAM4 model, which is originally written in Fortran, and it is still working within E3SM Fortran codes and also in CESM. And so to go from MAM4 to MAM4XX, we used modern C++, where we ported or modernized the code from Fortran to C++. Using COCO's performance portability library, so that, and the motivation behind that was we wanted to run the code on all flavors of GPUs, CPUs, or any future architectures that is coming into place. So COCO sort of sits, COCO is sort of a wrapper which allows us to run on different architectures without changing the code. So that was the motivation using COCO's and C++. And it is designed for next generation HPC systems running at really, really high resolution, which is like kilometer scale resolution. So that was the motivation behind this work as well. Like we want to run the models at really high resolution. And it is optimized for GPU platforms and enabled to enable high resolution simulations. But it was a journey. We had to take the code from Fortran, refactor the code so that we can port it to C++. And the next step was porting to C++. And the final step was like, once we have the whole code, the final step was to integrate it into EMXX. So here you can see we went from Fortran, which is MAM4 in EAM, which is E3S atmosphere model in Fortran, to MAM4XX in EMXX, which is a new model with different physics than EAM. So for MAM4XX, it was a new host model. And like I said, we use modern C++ and all the software engineering best practices like code coverage, automated testing, and all that. I'll talk about those in my next slides. So while refactoring the code, we took care of these things, or we kept these things in mind. We broke long subroutines into multiple very short subroutines so that we can enable tests. This is a no-brainer. And long subroutines often have mixed logic, so they are not just doing one thing. So we broke the code into smaller routines so that each smaller routine at least is doing just one task. This is again to enable testing. And of course, there are driver routines which will do multiple things, but most of the low-level routines were doing just one task. And of course, when you break the code or refactor the code, it becomes reusable. So we had that abstraction so that we can reuse the smaller subroutines. And it also makes it maintainable because you don't have like 10 different places to change. And we removed a lot of dead code. So there was a lot of dead code. Dead code means it is not invoked. That means it is never tested, so untrustable. So we removed a lot of dead code while in this exercise. And the philosophy was like, it's a true refactor. So we did not change the logic of the code at all. So we did find some bugs in the code, but we did not fix those because that would change the answers of the model. And then we'll have to engage scientists to make sure that model is still producing the right answers or expected output. So we did not fix, so bugs are baked in. And this whole refactor was bit for bit. So we didn't change the answer at all. And this whole operation was driven by test right from the beginning. We start with a test, and we have a test suite which will test for this bit for bitness for every change that we made to the code. And the next step was porting to C++. This, again, required very careful work where we go from Fortran and develop this C++ subroutines. And the problem or what we need to do here is to make sure that C++ code is producing the same answers as Fortran. And here we did not use bit for bitness. What we did was we extracted, because we have very, very small routines. And other thing we took care of is that all the small subroutines have data types which are primitive data types like integers, reals, and all that, so that it's very easy to write tests. And that also enabled extracting the data. So we didn't have any derived types. So it was all like arrays of integer floats and all that. So what we did was we ran the model, we developed a new infrastructure to extract the inputs of all the subroutines and outputs of all the subroutines. So what we did, we extracted the input for all the subroutines, invoked the Fortran subroutines with that input, same input, and invoke the C++ routines with the same input and expected the same answer. So that's like a very high level description of this infrastructure that we used. And we used some sort of tolerances to make sure that the model we didn't change the logic of the model. And so this infrastructure is fairly like extensible. We can extend it to any type of like multi-dimensional arrays and data types. And we extracted massive amount of data for any column, any time step. So we validated the code going from Fortran to C++ using this. And that also created a lot of unit tests for us because we were testing it. So we kept on using those as unit tests while putting the code. And the next step is to integrate the ported code. So we took the code and integrated with the EMXX model using interfaces. So this is the slide which shows how MAM4XX sits within EMXX. So this is a flowchart. This is just one time step of the model. And all the black boxes are existing processes in EMXX. And you can see shock, P3, which are P3 is microphysics, shock is macrophysics, and then we have other like RRTMG process, which is radiation. And MAM4XX actually interact at many different points in the time loop. So that's why we broke these MAM4XX into 7 different interfaces and hooked up in the time loop. And to invoke MAM4XX, we have a very easy comp set or a configuration set, which we also use in CESM models. And we can invoke the complete set of MAM4XX using this easy to use comp set. And we test the model at all resolutions that we have, like going from a very low resolution, which is 800 kilometer, to really high resolution, which is 3 kilometer. And the model works on all the DOE leadership class facilities. We have nightly test sets set up on all the machines like Frontier, Aurora, Perlmutter, and all these machines, they use different flavors of GPUs. So Frontier has AMD GPUs, Perlmutter has NVIDIA, and Aurora has Intel GPUs. So model works on all these machines thanks to Coco's performance portability library that we used to write the code. While going through the process, we went through many challenges, and I'm listing some of the challenges here and also listing like what actually helped us. So EMXX is a new model, so we didn't know what will happen if we hook up MAM4XX with this new host model because it's a new physics. So what helped us was the modular design, and we integrated each process incrementally. So one process at a time, we tested it thoroughly, making sure that it is producing their expected output. So that helped us a lot. So that's why we see, 7 interfaces here. EMXX originally has very limited I/O support, so it was not able to read a lot of different kind of input files. We extended that facility because MAM4XX or any aerosol schemes reads a lot of files like emission data, monthly data for various fields. So we extended that capability, and physics is untested at this high resolution. MAM4XX was never run at this very high resolution. So what helped here was hierarchy of tests. So we have unit test, regression test, bit for bit testing going over from all resolutions. So we heavily leverage testing here to make sure that the model, if it fails on high resolution, we can come back to low resolution and fix the bugs. And it's kind of hard to debug on GPUs, but this helped us a lot in locating where the problem is. There are numerical instability at high grid resolution. Again, here testing helped us a lot. We had testing set up for very high resolution on target machines. So that helps us detect bugs very early on. And since it's a parallel program, so we often run into race conditions. So race conditions on GPUs and code reviews helped a lot. People were able to detect or alert us like if something can go wrong. And we use vendor tools, compiler sanitizers like flags to check memory and all that. And variability across GPU machines. So we are using different GPUs. So we sometimes ran into problems, and we closely collaborated with the machine point of contacts and vendors themselves to get past those. And long simulations when we ran, they often would crash. So we had enabled testing for non-long simulations, nightly testing, reproducibility checks to make sure that if we crash, we can start from a point very close to the crash and then resubmit and figure out what is going wrong. So we didn't pay much attention to performance at this point because our main goal was to get the model port it to C++, running correctly, working in the EMXX framework. But here we have this performance plot. Here we can see the wall clock. I don't know if you guys can see my mouse, but on the y-axis, we have wall clock, which is amount of the time a process is taking. And on the x-axis, I have listed all the processes. And we can see aerosols is taking quite a bit of computational power. And of course, aerosols are pretty complicated, and we are explicitly modeling all the aerosol processes. So it is bound to take time, but we are still looking into the code. to improve the performance of the model. And here we can see we also added 31 new species in the model. Originally, model has just 10 species to transport. And MEM4 is an expensive process in the model. And ACI, which is the aerosol cloud interaction process within MEM4XX, is the most expensive process. These are some strong scaling plots. So it just means that if we throw more GPU nodes, we can get the performance out of the model. So which looks pretty good. It scales well. So we can use more GPU nodes if we want to run the model faster. And we also set up, just to watch over how the model is performing, we have set up these dashboards. So these are nightly tests. So we run the model every night and produce these plots. And you can see the time series on the bottom two plots where we monitor like how the model is performing with time. And this has been really helpful. And we are extending these capabilities to new machines. So it is already running on CPU machine, which is Compy, and GPU machine, which is Perlmutter. We are extending this capability to Frontier and Aurora as well. So this is my last slide. A summary. In summary, Emacs, this framework is now fully functional in the model. So we are able to run year-long simulations and also 5-year-long simulation with this model stably. So it runs very well on all different machines, CPUs, GPUs. And we have nightly tests set up on all machines, which are either E3SM owned machines or the DOE clusters, DOE machines. And as I showed, the performance model is slower at this time, but we are currently looking into the performance so that we can improve the performance of the model. And we are also doing some resolution sensitivity tests to make sure that the model, to understand how the model is performing at various resolutions, because with resolution, time step also changes. So there are processes with sub-cycle, super cycle. So we are taking those into account to learn more about how the model is performing on different GPU architectures. In terms of next step, I think for this and next quarter, we will be looking deeply into the performance and making sure the model is performing well. And we are also extending, like I said, the CI/CD performance dashboards with triggers notifying us if the performance really dropped after, say, a new change or inactive model development. And we are also adding new features as requested by the evaluation team. So that's all. Happy to take any questions.
Questions? Please.
So you talked about the conversion in 2 phases. So refactoring the Fortran and then the Fortran to C++. Could you comment on percentages of time for those? Which was the most challenging?
I think porting from Fortran to C++ is more challenging because then we have these validation tests, which we have to make sure that the code is producing the same answers as before. And refactoring, that aspect is still there, like we have to verify the answers, but we took the bit for bit reproducibility approach there, so it was not much involvement there for verification and validation. And also from going from Fortran to C++ involved COCO and porting itself to C++. So I would say that part was a little more involved than refactoring itself.
Okay, I have maybe a follow-up question to that. Like, was it a serialization framework that you used to like extract data from the Fortran thing and use them as inputs for both Fortran and C++?
So it was like what we did is we instrument the code, all the Fortran subroutines we instrumented, and we had flags to turn it on and off. And we would run the whole model, and it would extract the data, and then into a YAML format, and then we would use the YAML file to drive C++ testing. So we extract the data, we would run the model, and the model was running at really low resolution. So it was really fast and quick to generate data.
But was it like at a fine grained level, like for example, inputs to every subroutine
Yeah.
call? Okay.
Yeah, input to every small subroutines, because the data types were like primitive ints float, so it was really easy to capture that at the beginning.
So, thanks. Go ahead. Yeah, Chris.
I think you
Because, yeah, so for the, since you have the microphase ported to C++, and I assume you want to people stay with that version. And I see some scientists that they still want to use the Fortran code for their scientific development. How do you envision to address that conflicts, disagreement in this case?
So you're asking like the aerosol modelers
Yes.
developing code?
That they develop their scientific code, but they are more used to Fortran rather than the COCOs. What would you suggest in this case to make sure that the code can be developed but still remain in COCOs in the future?
Yeah, that's a great question. We always like had this question, and we often think that it is kind of hard to move Fortran folks to C++. And it is indeed, C++ is complicated language, a lot of templating, and but I worked with at least 2-3 people who were not trained in C++, and they were able to go into the code and change the code. So I'm confident people will learn. At a very low level, the codes are not that complicated, but there is of course a layer which people need to be aware of. But at the very low level, the equations, I think the scientists were able to go in and make changes to the code. So that is encouraging, and I hope it will stay the same way.
Thank you.
Very short, very impressive work. These bugs that you mentioned that you found, are you planning on addressing them?
Yeah. Yeah. So yeah, the motivation of course was like we didn't want to involve scientists in that. Yeah, but yeah, definitely.
Because it feels to me like in many models, there's so many bugs that people really don't want to touch them because it might bring all kinds of havoc. So
Now these were like indexing bugs where we know it is grabbing the wrong data. So we will fix that. Yeah, so that is something we have.
Let's thank Balwinder. Next up is Harvey Dam, PhD student at Utah, advised by Ganesh Gopal.
complicated name.
Okay. About time. So I'm Harvey. I'm a PhD student in computer science at the University of Utah. He is also in the next is our advisor. So this presentation is about a loss function, and if you didn't know, a loss function is a scalar function
you want to minimize. It's an objective function. And this function that we made aims to capture a topological difference. And there are different topological features that you can measure, but we're going to focus on critical points. So if anyone wants to nitpick my terminology, a critical point is a minimum or a maximum in some differentiable function. So it's where the gradient is 0 with respect to something. But when you sample a continuous function on a grid, you will maybe miss the critical points by the order of the step size, like your sampling resolution. So for our purposes, we're going to say that the critical points are just the minima and maxima of that sampled array of numbers. So what is the use of such a loss function? Well, suppose you have a compression method like MP3, and you take an input, let's say that's the white curve, and then you compress it, you decompress it, and you get the blue curve. Well, suppose you really care about where the direction changes or where it doesn't change direction when it should. You want to capture that and sort of isolate that with some other compression fidelity metrics that you might want to use instead. So is there some kind of function that can capture this and only this, and like ignore everything else that you want to ignore, so you have different knobs to turn? Well, yeah. But before I define that, let me just show you another example of something that can happen when you compress and decompress something, which is adding critical points that weren't there before. So you might have seen this as compression artifacts. That's what it's commonly referred to. Like if you look at JPEG images, you might see like these 8x8 blocks from like a low quality JPEG. So those are critical points that weren't there before that you may have introduced because of low compression fidelity. So we want to not add any and preserve the critical points that were already there. And where would you use this? Well, you would maybe use a learnable compressor. This is a diagram of an autoencoder. So an autoencoder just takes an input, has some model. Let's say for this image autoencoder, it's a convolutional neural network. The output is some latent representation that's usually much smaller than the input representation and the decompressed dimensionality. So once you have that trained, it should be a dedicated compressor for that particular data. So traditionally, we train autoencoders using some point-wise error metric, like mean squared error, which captures the square difference between each corresponding point in the input and the reconstruction. But it doesn't really capture anything about directional trends. So what can we do about that? Well, suppose we just count the sign mismatches between, let's say, the derivative of the original and the derivative of the reconstruction. And the discrete version of derivative is the finite differences. You just subtract adjacent elements. So element 2 from element 1, element 3 from element 2, etc. But there's a problem with that, and that's it's not differentiable. The sign function has discontinuities, and whether things are equal is also a discontinuity. So to deal with that, we approximate the sign function with hyperbolic tangent, and we put a hyperparameter with that sharpness, as we call it, S. And then we can vary the sharpness depending on how sign-like we want the approximation to be. This has turned out to be quite a problem in our implementation, because choosing the right S is pretty difficult. We don't really have a principled way to do that yet. Okay, so we have this approximation of the sign function. The rest is just like using absolute value instead of whether things are equal. So just for example here, let's say, I don't know if you can see this cursor. Yeah, so let's say one curve is going down and the other curve is going up. It would be like approximately 1 minus approximately -1, which is like 2, which is different from our original definition with whether the signs are the same. So a little detail in our approximation is we divide that by 2, so the units match up. But in the ultimate implementation in an autoencoder, you're just going to scale this by some coefficient anyway. So we leave out the division by 2. So pseudocode, in case you want to look at it. This mess right here just says you take the finite differences in each direction, and then you take the absolute value of the difference between the hyperbolic tangents. This division by 2 is what I talked about before. You don't need it. And then you add them up. So looks pretty fast, right? And it should be. But the time complexity and the memory complexity depends on what you want to prioritize. So you can either put this dimensionality multiplier on the sum of the log number of elements or the product of the number of elements. And maybe you care about different things, but we did it this way because this is lower complexity. And by the way, this is comparable in complexity to mean squared error. Here are some time and memory empirical results. So I think we cut this off when it took longer than 1 second per example. So you could see all of these other non-differentiable measures of topological dissimilarity kind of puttered out at like 2 to the 9 elements or something like that. Whereas our loss function, DSL, and mean squared error behaved better. And then memory also, you can look at it. So does it work? So we put some data through autoencoders. These are one-dimensional stock prices. Like, I think this was NVIDIA last year. So, I don't think it helped very much, but at least it didn't hurt. So the reason I think is because stock prices, the movement resembles Brownian motion. So there's a lot of randomness in there, and an attempt to preserve that randomness doesn't really make sense. So it doesn't do much better than mean squared error. If we switch to some other kind of data, so these are 2D natural images, it does better because I guess there's less noise in like natural images that aren't too heavily compressed. So here, if we mix in a little bit, like 1/8 of our loss function along with mean squared error, we get lower topological distance according to some topological measure. This is like the difference between persistence diagrams. There's merge tree distance and there's like pairwise correlation difference. So overall, the story is if you mix in a little bit of our loss function, you'll get lower topological distance. These others, SSIM and PSNR, they're applicable to this data set because they're natural images and these metrics are based on human perception. So even with these, higher is better in these. If you mix in a little bit of DSL, it'll look better. Okay, now this is some 3D data. Actually, is it 3D? I think it's 4D. It's like from a shallow water simulation. So you might have heard of that. One complaint we got from reviewers was that we were using synthetic data. So we've replaced this with data from NCAR, and I think that's already done, but I didn't put it in here yet. But same story here. If you mix in a little bit of DSL along with MSE, you'll get lower topological distance. This subfigure is split into channels because the merge tree distance tool that we were using, I forgot what it was, but it was limited to 3 dimensions. So if you put a 4D array in, it doesn't work. So we decided to just split one of the dimensions up into 3 channels. Okay, so summary is we have a loss function that characterizes the mismatches between the signs of finite differences between 2 arrays. It behaves like some non-differentiable, slow topological distance measures while being parallelizable and differentiable. So we're still working on this. There's a preprint. Let me know if you want to help out. I'd appreciate it. And yeah, that's the end of the presentation. Any questions?
Okay, Allison.
So for the NCAR data, I can't, can you remind me what fields you're looking at?
Drifty was very interesting.
So it's the era 5 data and it's I don't remember but I can visualize the information. It did work well for one of the combinations and it should have given the results to Harvey so he could actually get here. But yeah, I can share the results soon. We have one of the combinations of the other
Oh, input error.
yeah, the combination of those two, which gives good results. Yeah, like comparatively better.
Okay, so basically it looks like this, right?
Similar to these, it looks similar to these. But yeah, a combination of it works well on one of the fields. That's, I don't know the full form, but it's PV in the data set. It's called PV.
Pressure or some kind of.
Yeah, maybe related to that.
PV.
Reproducibility.
Yeah.
No, especially.
We'll definitely need help. If I can, since there is some time, I thought I might include a comment. I've been trying to follow the topology-preserving lossy data compression methods a bit, and this area has been growing in different ways, but many of the earlier compressors were not easily parallelizable. This probably is a bit more easy to parallelize, but it doesn't have the same criteria that it goes by. So any input you can give in the space, feedback as to where you find topological data relevant in your own data sets, that will really help us because I want this technique to work somewhere in a useful way. Yeah.
Okay.
Any others? Okay, thanks, Harvey. We are slightly ahead of time. We can start on the next talk now and then drink earlier. Okay, that's good. Thanks. The next talk will be by John Halley Gotway and METplus. Happy to listen in and understand. Thank you.
Thank you. Okay. These have been great talks, very interesting. Wide, and I'll echo Michelle's comment about verification. I didn't even know, I wasn't even aware of this more formal type of verification. So shifting gears back to Michelle's talk earlier, I'm going to be talking more about the engineering behind the METplus software. So much less about the functionality, much more about our engineering process. Kind of a show and tell of what we've been doing, sharing of best practices at NCAR. So my co-authors are, Michelle is listed there, of course, and then also George McCabe, who's sitting up there in the back row, and a few other software engineers who I work with on the various components of METplus. Michelle mentioned that, well, okay, I'll talk about that later. So this is community software, so fully supported to the public. And there's a lot of aspects of community software that I want to highlight here. So usually funding is available for new features. You know, what's exciting, what's new. But there's a whole lot of other things to consider when doing a great job with community software, including what sort of version control are you doing? How are you handling continuous integration, regression testing and test coverage, continuous deployment through containers and Conda, code quality. We've been using static code analysis tools and working on optimization, security scanning of our Docker images by assessing common vulnerabilities and exposures, and also a new acronym for me from working with the Air Force, or STIGs, Security Technical Implementation Guides. They have a whole set of requirements for making sure the software they use is secure. Deciding how you want to do development and release workflows. So handling new features and bug fixes. How do you handle internal communication through emails, meetings, Slack, that sort of thing. Handling project management, documentation, both for users, contributors, and developers. and then doing user training through online tutorials, pre-recorded videos, live sessions, and providing support both to their direct sponsors and to the broader community. And how do you do user outreach and marketing to try to encourage the use of your software? So the trick is figuring out how to take that funding that's focused on new features and functionality and leverage it to do a good job in all these other areas. And it's been challenging over the years. So Michelle showed this slide earlier, or this diagram earlier. So METplus is this thing on the left with a bunch of little cartoon figures in there. I'm going to be talking mostly about the Met software, which is this represented by this wire diagram. So I started in 2004 at NCAR, and our first release was in 2006. So over the years, there's been a growth of functionality, both in the number of tools and the functionality of each tool. Each one of these little ovals was it represents an executable, and then the gray boxes represent I/O. I could have never imagined that when I made the first PowerPoint slide in 2006 that I'd still be presenting this silly figure 20 years later, but that's the way things tend to go. So in the same way that there's a growth of functionality over time, there's an evolution of the tools we use to, oh boy, that looks bad. Oh, that's too bad. Okay, well, those are supposed to all be all in one line, those dates. So over the years, we've evolved our version control system from CVS to Subversion to Git. Our testing, we started with shell scripts that we run on a local Linux machines, and in 2020 or so, we transitioned to using GitHub Actions. We used for project management, Jira, and then onto GitHub projects. Our documentation started in Word, and I remember, we had a 300-page user's guide, and if you went to try to save it on your laptop, it would usually crash your laptop, or it was like 50-50. So we moved on to Lix, which was a LaTeX-based documentation, which was transformational because then the docs could live with the code, which was hugely important. And then we evolved to using Read the Docs in 2019. We started creating DOIs, digital object identifiers, through Zenodo shortly thereafter. That enables folks to easily reference various versions of your code. And we began scanning the code for static code analysis using Fortify, and then moved on to SonarQube. This was at the prompting and funded by the Air Force. And we, just in the last year, started using Gripe to scan our Docker images looking for vulnerabilities. And then we distribute our code. Obviously, you can download it via Docker or via GitHub, but also via Docker. And then George, big kudos to him for getting our Conda build working in the last year or so. So that's been great. Not shown here, but also important is user support. We started with email. We switched to an RT ticketing system, and then back in 2020, we switched over fully to GitHub discussions, which it's great to have the history of the discussions publicly available so people can find answers to previously answered questions. So how is this organized on GitHub? We have so the DT Center is a shared organization with staff working at NCAR, NOAA, and the Air Force. And so rather than housing our code in in the organization of one of those organizations, we created our own for the DT Center. And that DT Center organization on GitHub has, I think, 42 repositories. The majority are related to METplus, but there's other ones for other activities of the DTC. The Met-based image repository is a very simple one, but it provides basically the Docker image in which we do our development and testing. And one of those images feeds up through Met, and then METplus is layered on top of it. The METplus analysis tools are split across the Met viewer, which was used to create many of the plots that Michelle demonstrated. MetPlotPy, CalcPy, and Data.io are other components of METplus that feed into MetViewer. And then there's also at NOAA GSL, the MetExpress package leverages MetCalcPy and MetData.io, I believe. So, and also talk about these 7 other repositories, METplus-action- yada yada. These are custom actions that we use in our GitHub workflows. I want to point out that we qualify as a nonprofit, and as such, we enjoy a lot of benefits. So I looked at our usage, or tried to quantify the benefit we receive. I think in about the last year, we've saved about $10,000 in our free access to GitHub Teams for 77 users, about $6,000 of GitHub Actions that we otherwise may have had to pay for. Our use of our participation in the Docker Hub open source program for 10 users is valued at about $2,000 a year, and our use of Slack Pro for 23 users is also about $2,000 a year. So although even though we get these, we enjoy these benefits for free, they're hugely worth the investment of $14,000 for our productivity. So definitely worth it. I want to spend a little bit of time talking about our documentation, and because this is really the first place that users engage with the software. So here is just a snapshot of in the METplus repository. We have 4 different guides that are housed there: the contributors guide, release guide, users guide, and verification datasets guide. I'll point out that we have set up in our pull request template a standard question to say, do these changes include sufficient documentation? So basically, when you propose changes to the code, we're requiring you to update the documentation at the same time, which has been fantastic to keep the code and the documentation in sync. So METplus consists of these many components, and while these four pieces of documentation live in METplus, we're pulling in documentation from all these other repositories. Julie Verstopnik in the last year or so figured out when read the docs how to create a project where you're pulling in documentation from multiple repositories and serving that in one place. We asked users, and they said they didn't even know that the user's guide for all these other repositories existed. So by putting them all together in one spot, it's been very helpful. This may seem a little over the top, but we have this release guide where we first define the different types of software releases we create, and then we provide a checklist for every, if you're going to go create a release, here are the steps to follow. And for example, Michelle mentioned we're creating a new release this week. I use this all the time. At first, I thought this wasn't worth it, but it has totally been worth it. If you want to do something in a repeatable way, then write it down and get organized. And I'll note that even though there's many of these release steps are common to all the releases, we've organized the repository in a clever way. So we define each individual release step, and then we just include them in the right order, so that we don't repeat ourselves. I want to spend the rest of the time talking about how we use GitHub Actions. And here I've just listed the main METplus repositories and the number of workflows that are defined for each one. And since I work primarily in the Met repository, I'll talk about that one. So we have 8 different workflows defined here to achieve eight different tasks. And I'll highlight a few of them in the future slides. So one of the requirements from the Air Force was that when we create a release, they need to have a checksum to ensure that what they download from the website matches what we put up there, or what was intended to be put up there, so that they, for security concerns. So GitHub automatically serves up your source code in zip and tar format. And the things that we've added here are the checksum files. And so this is done through a workflow, and I'll highlight that this workflow is triggered every time a release is published. And what this workflow does is it calls this METplus action release checksum that actually George wrote. And it's pretty simple. It's a Docker file that has an entry point script. And if you dig down in that entry point script, you'll see this call to SHA-256 sum to generate the checksum file, which ultimately gets added to the release. But just demonstrating that, the mechanics of how this works, since we have several different code repositories and all the releases need a checksum, it made sense to write a custom action and reference it in all these repositories. I'll note that if we were going to redo this, we would do it in a little bit simpler way. but this, when we wrote it the first time, that using the Docker file was kind of the standard way of doing it. And so it still works today. Next, I'll mention the documentation workflow. So we want to make sure that when we update the docs, we're not introducing warnings or errors. And so before, in the last one, it was triggered by the creation of release. This is triggered by lots of stuff. So every time we push to one of these branches that meet these names, or we create a pull request, as long as we've touched the docs directory, then this workflow gets triggered. And I'll highlight, in this case, I'll highlight this last word there, the workflow dispatch. That's the last triggering event. So if you were to go to the repository and look at the actions tab, look at the documentation workflow, you see this run workflow option. So you can manually trigger it, and that will launch it for whatever branch you select. And a minute later, the workflow will have run. And one nice feature is that the artifact contains a rendered HTML. We seldom actually use this, the artifact with the rendered HTML, because we use read the docs, but it's pretty easy to introduce warnings into the restructured text files of read the docs that read the docs uses. So having this workflow has made our lives easier, because it lets us know as soon as we screwed something up. The testing workflow is the most complex across METplus, and I'm not going to go through all the details. In fact, George gave a great talk at the NCAR Software Engineering Assembly workshop a couple years ago, going through in great detail what it does. I just want to point out an aspect of GitHub Actions where you can set up kind of conditional execution. So in this case, I've run the testing workflow. The wire diagram represents all of the possible jobs that can be run. Since I'm just pushing to a feature branch, all it did was it compiled MET. So in GitHub Actions, it said, does the code compile? Yes. Okay, we're all good. If I'm running this for a pull request, then I'm actually going to be, then all of the unit tests will be run. And so here you see I've compiled the code, I've checked the input data, all these tests run, this matrix of unit tests. We've checked for differences by comparing against previous truth, and there's no differences and everything's great. With a different run, maybe we found differences. So maybe all the tests ran, and then you get the red X that the checks for differences. Differences are found. Those may be good differences, because maybe I changed the code in a way that I intended to get differences, and that's great. And now we get the human involved and go make sure that those differences are what we expected. Or maybe if I run again, maybe one of my jobs failed, and that's almost never good. I can't think of a time when you want the job to fail. So this has been hugely transformational to the way we do software development on the METplus team, and it has been invaluable. You can see, so when this happens, which it does, often enough, I'll go look at the artifacts, I'll download the log files and the output, and I'll go figure out where the differences are from, and quickly I can get to debugging it. Okay, another issue with having code spread across many repositories is integration testing. So if I make a change in MET, it certainly can break use cases in METplus in ways that we don't expect. Even if all my unit tests pass, I can still break the functionality of the larger system. So this is set to run in MET whenever I change one of these special branches. And we say that the develop branch is special, and so are the branches beginning with main_v, so main vx.y. So for each official release, we create a new main branch. And anytime we update it, that's important. We want to test. So although if it's a documentation only change, so paths ignore. If it's docs only, we don't really care. We don't need to test for that. So what this workflow does is if we've changed one of these special branches, then we call this custom action, trigger use cases. And what this does is if you go look at that custom action, it uses here GHCLI, so the GitHub command line interface. It sends a trigger to the METplus workflow to go run all the unit tests. So we build the new version of the Docker image for this component. We go tell METplus to go run the 100 or so use cases. Go compare out the new output to the previous output and let us know if we've accidentally broken anything. This also has been hugely impactful because it happens a lot where you have unintended consequences. All right. We have been distributing our code through Docker for a long time. Here I have a snapshot of the METplus version 6.1. It was built in July, but you'll note it says it was last pushed 2 days ago, whereas METplus version 5.1 was built 2 years ago, was released 2 years ago, was last pushed 2 years ago. So with Docker Hub, you build an image, you push it up to Docker Hub, and it just sits there, right? And in the meantime, what can happen is that vulnerabilities can start accumulating in the packages that are contained within that image. So it's frozen in time. We've realized that we should start providing routine refreshes of those images that we're supporting. So in the last year or so, we created this new workflow to update the released Docker images. So this runs, and I want to highlight here that you can run workflows on a schedule. So here it's like running a cron job. So, oh wow, though, I'm sorry about that. That was all lined up on my machine. Okay, so every week we regenerate the Met base images, and then 3 hours later we regenerate the Met and Met viewer images, and then 3 hours after that we regenerate the METplus images, only for the most recent supported versions. So that way, when a user downloads an image and uses it, it will be at most a week stale. So along the way, we learned about scanning these images for critical vulnerabilities. We've been using a tool called Gripe to do so. And so this is the weekly scanning we do, pointing out that, for example, when we scan the Met viewer image, version 603, we found no criticals, but we found 41 high CVEs, whereas in Met viewer 610, we found 5 criticals. So basically the Air Force who's funding this work has directed us to eliminate all critical and high CVEs. And so we're in the process of doing that. This is new direction as of a few months or so. But basically by setting up a scan every week, we can know when we come to the office on Monday if we got work to do that week to fix additional CVEs that were found in the Docker images. And that's it, right at 20 minutes. So thank you for your time.
This is probably just a clarification because I think you explained it, but I was just curious about the workflow you had where, like when, like merging a PR into Met then triggers a workflow in METplus. So sorry, can you just explain that again one more time? So yeah.
So here we go. So here, let's say this actually just happened today. Like I leaned over to George and said, "Hey, did that trigger work? Like that run in METplus?" So I merged something into the main v12.2 branch of Met. And so then that was a change. It was a push to this main v12.2 branch, which triggered this workflow to run. And so the workflow used the METplus action trigger use cases. And so that action runs this. It passes information about which repository has been updated and kind of the George could probably explain this better, but it passes the information to the action, and then ultimately we use the GitHub command line interface to send a trigger to METplus to go run its testing workflow using the updated version of Met.
And sorry, so is it grabbing, this is probably, is it grabbing like the hash of the latest version of Met or like from on GitHub itself, or is it grabbing like a Docker?
It's grabbing the Docker image.
Okay.
The updated Docker image. George, is there anything you want to add?
No, I think there's some information on the bottom left of the triggering. So it's the repo that triggered it, the commit hash that the changes, and the person I think that made those changes, they contact them.
And this is all fully public, so you can go snoop around as much as you like.
Oh, yeah, 'cause I kind of definitely want to steal it. So yeah, cool. Thanks.
So let's thank the speaker again. Last talk is by Deepak Kumar on Earth system software reproducibility. Thanks.
Hi everyone. So today I'm going to give a glimpse of non-coder perspective of reproducibility of the software in for the weather climate analytics. So although I'm not from the coding side, but I'm trying to understand that how it will help the weather and climate domain in this sector. So sorry. So, coming to the background, so in weather and climate forecast also we are concerned with data models analysis and results. So, although we are having a huge amount of data and different types of data set in this sector, and we are using different model like processing model, and apart from that, we are having forecast model, and using those model we are using some results, and sometimes we need to verify those results in a way that it should be applicable to different data types. Like sometimes we are running the models for GFS data set, and the same models we are requiring to run on ERA 5 data set. Likewise, the basic motivation for this work is the spreading of extreme weather event. If you see the left side of my slide, that summarizes the context that there has been increase in different type of weather events, especially climate disaster. And if you see the quantitative form of that, it says that if a person has taken birth in 1916, and if the same person has taken birth in 2020, so there is a chances of 3 times increase in different extreme weather events, whether it is wildfire, river flood, crop failure, drought, or heat waves. Similarly, if you see the right side, so there has been increase in different heat waves across the country, and the data is being shown for 2022. So beyond that, the basic reason behind this weather forecast system is that there has been huge investment in the sector, and there is a projection that there will be 7% of increase by 2029, and the basic reason behind that is increase in the technology improvement and policy support from different government across the globe, and there has been decrease in the cost of different equipment also, if we compare from the earlier side. So the basic requirement for this weather and research forecast is to analyze the impact of a different weather event or extreme weather event on different sector. So if we need to understand the impact of this weather event on different climatic disaster, we need to run different simulations on that. And it may be useful for, or it is useful for different sectors. Like if you see whether it is energy sector, whether it is a construction industry, government department, or whether it is emergency services, like in the case of what I said, extreme weather event. So it will be applicable to all of the sector. So due to that reason, we are more inclined to understand or to know about the weather forecasting in this. So why the reproducibility is difficult in our system science? So the major concern here is that complexity of different Earth system models, because for if we change the domain, and if we change the multi-scale interaction between different models, it will change the whole result. And apart from that, we do have data challenge. If we compare ERA 5 and GFS data set, so even we change the data set, our resolution of the result will also change. And apart from that, we do have issues with computational environment and natural variability of different data set apart, and different models are also there. So if we see the basic component of this Earth system science for weather and climate modeling, so we are having different models for each one of the component, whether it is a atmospheric model, ocean model, and apart from that, that is being coupled through a certain interface which help to visualize our generated result. And apart from that visualization, we are also doing the different weather and climate insight to those data set to understand the impact of different disaster. So if we see that why reproducibility matters in this sector is that first thing is that whatever the models we have generated, so it should be dependent on these four pillars. One is verification and transparency. Second one is computational research. Third one is accuracy of the data result or method, whatever we are generating. And apart from that, process integrity among different segment of the work. So if we see the verification and transparency, the important thing is that we should be transparent about the methodology and why it is important to reproduce, or why it is important to confirm the finding and reliable results. So whatever the models and data we are generating, it should be open, openly accessible to different user groups, so that errors in our data models or result whatever we are generated should be easily verified. And apart from that, there is another concern regarding computational research, that whatever models we are generating, and so that should be tested with different user communities, whether it is energy sector, whether it is a planning sector, or whether it is a disaster sector. So that is another part of that. And if you see the accuracy of the data set or result what we are generating, so it should be easily verifiable, so that it will not give any misleading result to that. And last but not the least is process integrity. So in that, uh, uh, whatever scientific method we are generating, it should be reliable and it is free from any kind of bias. So that will integrate all the different segment of the work. So summarizing the challenging in the reproducibility in this climate and weather field, if you summarize into key points, so there has been variation in the computational environment. Like if we change the model, we need a different hardware like CPU and GPU, and even the software version changes, like from one platform to another platform if we are migrating, so it is giving issue with running those models. And there is a lack of comprehensive documentation, and there is a lack of version control in different open source software. So that is another part to that. And apart from that, there is a dependence on proprietary software and the data set. There are certain programs which are proprietary, and that is not accessible to open user community. So that is also one of the factor to that. So if we see the current state of reproducibility in the Earth system software, so first issue is fragmented practices, that different research group are using different kind of languages, like someone is using Python, someone is using Fortran, someone is using C. So that is also one of the biggest problem in testing and validating the data and method what we are generating. And apart from that, there is limited adaptation to FAIR principle in this domain. And there is also various kind of tools that are available, like WRF, CSM, or ESM validation tool. So due to that also, that is giving problem. So coming to the main part of my one of the case study that I will discuss with you, that is more inclined to WRF, and I have used this WRF for understanding the spread of wildfire in the Texas region. So that I will be showing in the upcoming slides. So giving context to that, if you see the 10 countries with largest forest cover as per 2023, so USA lies at number 4, and we are having almost 300 plus million hectares of forest cover. So there is a huge chances of severity to the forest fire. So that is one of the concern that I have taken this forest fire as a case study. And apart from that, if you see the different states that is more prone to forest fire as per last year data set. So California and Texas is one of the most prominent state that is more prone to the forest fire. And if you see the economics of those, so that is disastrous. If you see the current year, so it is giving loss to $150 billion loss to in Los Angeles wildfire of the current year. So in order to understand the spread of this, we are more concerned in mapping the fire risk to different regions, and we should be able to map whole nation like this, and apart from that, we should be capable of means pinpointing to the local level, whether it is a state level, means whether it is a state level or whether it is a county level. So we should be able to locate to different regions. So based on that, the different user group have already divided the whole nation into different fire risk zones, and different seasons that that are more prone to fire risk. And that is also means comprehending that there are 4 factors that is more triggering to wildfire to those reasons. So one concern is rising temperature, another one is increased drought, and one is extended fire season, and third one is fuel aridity. So in order to understand this thing, we are running the high resolution WRF model in HPCC, and we are post-processing those data set to understand the location and propagation of forest fire in the Texas region. So first, we have taken the data set from JFS system. We have run the WPS, and after that, we have run the WRF. And later on, we have done the post-processing. And in post-processing, we have done the hourly visualization of the data set like this. You can see in this slide that on one side, we have shown the propagation of forest fire at different hourly time scale. And other side, one of my research group, means one of my research mate is working on the same thing on daily basis, wildfire growth using machine learning approach. So the results are somehow looking like this. You can see that we are able to locate the probable locations of wildfire where there are chances of for wildfire happening, so that the emergency manager or the rescue team can go to those locations, and they can take necessary measures to those things. And we are also trying to integrate those data set with different other co-located data set, so that we will be able to give a better visual understanding to different user communities. And based on that, there are certain suggestions for improving the reproducibility, because there are many people who are not from the software background, so they are not having good understanding of all the software development, coding, and testing. So better is that containerization of the codes can be done, and version control should be there, so the non-user group can understand that what changes has been done to code. And fair principle can be adopted for the same thing, and open data and code sharing should be there, so even a non-coder can go through these code and they can understand that how those thing is being done. And apart from that, community driven reproducibility can be done for sustainable science, that a group of non-user community members can be engaged to that, and that can help in reiteration of the code. So all are working in a feedback and collaborative manner. And the major impact of this will be on policy making, disaster management, long-term climate planning, and of course on reproducibility. So this is the conclusion and future pathways for that. So it is one of the technical and cultural challenge also, because some user group are not in well versed in a particular technology, and apart from that, there are certain countries where there is no funding support. So there will be no uniform working of this software development, or maybe the testing part. So they may lose the actual amount of testing of this thing. And there has to be a fair principle in order to develop more usable form of the codes. and it will have a long-term impact of most of the sectors, whether it is energy sector or whether it is a disaster sector. So any sector will be affected to that. And apart from that, it can be integrated to different systems also. And coming to future pathways, so there should be some matrices for software regulation like WRF or WPS, or maybe some future development that is going to be happen. So thank you.
Yes. Let's start with one, which may be very open-ended. How will we ever do active mitigation using aerosol?
I think we can take the models and we can see the spread, and we can also model the movement of those things, and based on that we can take corrective measures that we can monitor that.
Going to ask when Palmika presented, I mean, is your aerosol simulation models may come in handy if we actually do active mitigation. I am a novice, but I listen to all the questions being discussed. And it may happen without our control. I mean, for aerosol is a big thing, and Jim Hansen's recent papers and books. I actively listen to popular science videos and all that. But yeah, coming more to your point, I think these are eye-opening charts, and I'm going to show it to my undergraduate class. They're very aware of it, all these things. But more questions here. Deepak. Yeah. All right. Anyone on Zoom? All right. Okay. Thank you so much. And Allison and Alper may say things about what's going to happen. So thank you.